I'd like to welcome everyone, people here in the audience, on-site in Stuttgart, and also everyone on-site, or not on-site, online, on the web. I think we have many registrations. We have like, I don't know how many people we have here. I think the room is pretty full. We have many hundreds applications online, so I'm not sure how many are joining us now, but it's actually a pleasure for me to introduce all of you to our information day today. It's about GISSMO and damage and failure modeling. And as usual, I always try to kind of start the information day with some more like a personal experience, with a very personal story. And, you know, like people who know me, I'm cycling a lot. So basically I use my bike to go everywhere. So one day I was just going through the forest, like in the middle of nowhere, and I was pedaling uphill. And then I noticed some kind of wobbling feeling on my legs close to the pedal. And I was kind of checking it and I was like, okay, there's something loose on the pedals. But anyway, I was somewhere nowhere, so I kept on pedaling. And at some point, my pedal came off. Yeah, and then at home, I disassembling my crank, and by taking a closer look, I saw this one. I think you cannot see anymore, but yeah, you see like there's a huge crack on the crank where the pedals are attached to. Yeah, and actually this is a personal story about damage and failure. Yeah, and to be honest, this is not the only time this happened to me. I had other instances where this happened. So my crank just broke somewhere. It just happened, broke, or the same applies to my chain, also came off. Yeah. So the thing is, I'd like to think about this as I'm super strong and I'm just breaking all the materials. Yeah. But the truth is, actually, most of the time I just drop my bike too often. So usually when it drops, it falls on the pedals and the crank first, and then you have some micro cracks, which is then eventually going to break the whole crank. Yeah. So, but that's the truth. But I like to think about like, I'm too strong for the material. Okay. Okay, this is a very personal story. And I was just checking the web. So it makes sense that if you think about damage and failure, it's like one part in your overall integrity of your whole structure or your machine you're going to deal with. Yeah. And then I found this video on the web. Yeah. So there's this guy, he built a machine and I'm not sure. I mean, you see all the wobbling and I'm pretty sure this is what he wanted to do. And you can see, since he did a proper assessment of damage and failure through simulation before, you see like, even though we have strong deformations and wobbling, the structural integrity stays intact. So it's not failing, yeah. So, I mean, to be honest, I'm not sure what to think about this video. I mean, I have mixed feelings about this one. So first of all, I'm pretty happy. I was expecting the worst at the end of the video. And luckily nothing happened except him spinning around for like 180 degrees. Yeah. On the other hand, I'm feeling so sorry for him. I mean, he spent so many time and so much efforts, I think, in building a helicopter. And at the end, he just built a complex machine, just turning him around by half a rotation. Yeah. So all efforts, but yeah. So, but anyway, so what I want to point out is, like structural integrity, one part of structural integrity is the assessment of damage and failure. Give you a more like a bigger example. Thinking about manufacturing processes. Yeah. So when you have a part in your machine or your structure, it could be a car, it could be something else. You're always using non-virgin materials. So the material you're using or the structure you have has undergone some kind of history. Yeah. And part of this history is the forming process in it before. Yeah. So for instance, if you have a sheet metal, you need to form it. And part of this forming process, of course, you're changing the shape, which introduces plastic strains. You probably change the thickness distribution of your sheet metal. But also the other part is that you're going to have some damage, micro cracks, which is kind of degrading the performance of your overall structure. So it makes sense to take all the whole process into your final structure, which you want to analyze and think of. Yeah. So damage or prior damage before you even build your machine or your structure, your car, whatever, yeah, is an important factor when doing this. Yeah. So basically what we're going to do is distinguish the whole failure into two parts. First, we have the damage. Yeah, the damage basically is considered as a degradation of the material properties or material performance. Could be think about microcracks, if you think about metals. Could be aging of plastics. Could also be crystallization in plastics. Could be corrosion and these kind of things. Yeah, so these are degrading the performance. Yeah, and then at one point you kind of leading this to failure. Yeah. Okay. And you have this in many materials. You have it in metals. Most of the time, metals you have microcracks. which are degrading the performance. Thinking about plastics, you have crystallization or aging. Think about foams, depending on the solid skeleton, you have either microcracks if it's metal or crystallization and aging if it's a plastic material. Think about composites, you have delamination, which you probably don't even see from the outside. And this is the most dangerous part in composite materials. So the assessment of prior damage in composite materials, you don't see it. Concrete or brittle materials in general, you have microcracks, and rubbers, again, you have this aging or crystallization processes you need to account of. This is, of course, a quick summary of the damage model we're using. I mean, it's quite famous now, the name GISSMO, which is an acronym for Generalized Incremental Stress State Dependent Model. And I'm not an expert at all, so this is all I know about GISSMO. And the thing I actually know is that's a damage model which leading up to failure at some point. But luckily, we have a lot of experts here today which can tell you more about GISSMO. And Filipe afterwards will give you the first introduction into GISSMO. So I think he will tell you a little bit more about this one. Okay, I want to give you a short history about damage modeling. So it started like almost 20 years ago. Usually people, when modeling damage in metallic structures, they were relying on the so-called Gerson model. And the idea of the Gerson model is to consider microcracks as some kind of voids inside of your structure, so which are growing over time. So this is the basic idea of this one. This formulation has then been improved by Frieder Neukamp and Daimler, developing the first GISSMO model, which is then further improved so that then we have conference papers, we have an official implementation as LS-DYNA, and then we have the so-called triaxiality concept. And basically what it does is relating the failure to the stress state we're having. So you can always characterize the stress state, how much is it related into the individual directions, and then based on the stress state, you can evaluate, define different failure criteria and assess different damage properties to it. And then we move on and then implementing different features. We also have anisotropy nowadays, which was back then referred as extended GISSMO or eGISSMO, but I think this name has disappeared nowadays. And then, of course, we brought this damage GISSMO model into this concept of modular design in LS-DYNA. So back then it was part of one material model, but with this add damage GISSMO, we can add the failure model of GISSMO to any kind of material model we have in LS-DYNA right now. So let's think about this as a more modular design in LS-DYNA. And then, of course, further implementation improvements such as temperature dependency and so on. And then since then, a lot of development and more people jumping onto the train of using GISSMO for their structure simulation. Okay, so this is an overview of what we have today. Like I said, many of my colleagues will talk about GISSMO. They have a lot of experience. They're working every day with GISSMO. Filipe probably is maybe one of the most experienced persons here at DYNAmore, but also my colleagues Sergio and David. David is more from the testing point of view, and also my colleague Cristoph. We'll talk today. We have a couple of breaks in between, so feel free also to use the time to network, talk to people, and so on. Also, this is directed to our audience online. I also want events. The first one is our user day in 16th of October in Stuttgart, and also the international conference on 22nd to 23rd October in Detroit. And if you have something to contribute, maybe after the day you have some inspiration, you want to do something, you do something, and then you may contribute as well. So with that being said, I think I want to introduce my first speaker, Filipe. So Filipe is from Brazil. He was studying
All right. Then first of all, thank you very much, Mike, for the nice introduction. And today, can you hear me well? Is that okay? Good. And today, my presentation here, it's really an overview about GISSMO, because we noticed over the years that GISSMO has become so big and a lot of features that it's difficult now to know everything what's going on there. Even for advanced users, they don't know some of the features that we have there. So we thought that might be a nice opportunity to really go through the keywords, through the flags, and show you what we have there right now. But before we start, let's go one step back and let's talk about what GISSMO intends to do, which is to predict ductile failure. Now, ductile failure is when you have, like in this example here, let me see if this is working. I think I have to change this, just 1 minute. Okay. Okay, now it's working. Now, in this case here, we have a dynamic case where we have some ductile fracture, right? So ductile fracture or ductile failure in the sense that you have some plastic straining or a lot of plastic straining before it fails. And that's what the intention of GISSMO was in the first place, be it a dynamic case like in this one or even a quasi-static case. It doesn't matter. But we should think about this from physical point of view, that this is not an easy problem. That is a complex phenomenon. And it has a lot of interdependencies or dependencies that you have there. For instance, the dependency of the plastic strain, dependency on the loading type. So it means that if you have shear or tension or compression, your material behave differently. You have a strong dependency also on the loading history, which means that if you have first tension and then shear until it breaks, if you reverse that loading history to first shear and then tension, you will have a different behavior there. That's what we typically see in experiments. And then you have other things like instability, localization, strain rate dependence, temperature dependence, pre-strain, pre-damage, and so on. So it's not an easy problem, and we should have this in mind when we see all the features that we have in GISSMO. And this would be like for just one material with perfect properties and everything, but then we have material scattering, so the materials are not constant in their properties. And when we go to the simulation, we also have all the numerical aspects that come with this. If you're using shells or solids, under-integrated shells, fully integrated shells, and so on. So the problem that we try to solve here is definitely not simple. And I think GISSMO is a kind of reaction to this complexity. Now, let's talk about GISSMO. And first of all, I know it's going to be a lot of information today here about all the flags and all the possibilities, but since we are recording this, you can watch this later again if you want to, I don't know, see something again, what we are talking about here. And in the heart of GISSMO, well, GISSMO is a failure and damage model, and you have the damage accumulation, as I have here in this equation. And this damage might affect the stiffness of your material or not. It depends on how you have it, how your settings are in the model. But basically, and that's also the criterion that we have. So when damage is equals to 1, then you have material failure. If it's below 1, you have no material failure. And this damage is driven by the failure curve, which can be, for instance, in the simplest case, as a function of the triaxiality as we have here. And it's also driven by the plastic strain. You can also change this in the meantime in GISSMO, but that's the heart of GISSMO, all right? And then, depending on how you set this up, you can also have an instability curve, and there is an instability measure by this letter F, where you have a similar accumulation there. And when this F is equals to 1, you have what we call the coupling between damage and stress, and then you will have a reduction of the stiffness until it fails. But it doesn't have to be like this. I have here 2 examples on this diagram. The first example where we reach at some point the instability or the beginning of coupling until it fails. So we have some reduction of the stiffness of the material, but you may also have something like this case here, where you don't have reduction of the material stiffness. If you want to know more about the theory and the ideas behind GISSMO, I suggest taking a look at the PhD of Frida Neukamp, who was the guy who invented GISSMO. It's available in the internet. It is in German, but I think in the meantime, we have very good translation tools available, so you can also translate this to take a look at this. And a few years back, we have also written a paper on GISSMO in the International Journal of Fracture, where we also give some more things about that. All right, now let's take a look at the GISSMO, and here I really go through each flag and tell you what is inside it, what is the purpose of it, and I will try to be brief in each one of them. But just to give you really an overview. First of all, GISSMO is really a modular concept, which means that you can add the GISSMO to virtually any material model in LS-DYNA as you want, right? So GISSMO doesn't even know what you are coupling that with. So it's up to you to be sure that you're making a good coupling. And this coupling is done through the material ID. So let's start with the first flag. The first flag is D-type. And D-type typically is 1. I think in most cases people are using 1, but it can also be 0. And when you have 0, it means that you have no element erosion, you have no coupling. And one important thing is that it can grow beyond 1. Yeah, which sounds a bit weird at first glance. How is possible that damage can grow even beyond 1? 1 is failure. It turns out that some users and some customers which are using this, they use this overshoot of the damage as a parameter in their design procedure. So that's why we have it here. So if you have like a little bit above 1, it means that you are very close to failure, or a little bit above failure, but you have 4 or 5, it means that your design is really much above the failure. So that's why we have it like this. If you have D-type to 1, it means that you have element erosion and coupling, depending on how you set up your model. So here you can see that the elements are getting eroded. If you want to deactivate the coupling, coupling is per default always active in GISSMO. So if you want to deactivate this, you should set decrete to 1 and ecrete to 0, and then you get the coupling deactivated. And finally, the equation of GISSMO here is a function of the increment of the plastic strain. But if you want to change this, if you want to use another variable to make the evolution of damage, you can do it. For instance, let's say that you want to use the history variable number 6 in your material model. You should just put a 6 before the 1, and then you can tell GISSMO, okay, I'm using that history variable to drive my damage. And I've seen some customers using this feature even for applications that I was not expecting. For instance, airbag simulation. They thought GISSMO is so flexible, let's use this for airbag simulation. It was not the intention initially of GISSMO, but if they can have good results with that, why not? Yeah, so GISSMO can work in that way as well. Now, the next flag is ref size, and ref size, it's a bit complicated. I will wait until slide 15 so I can explain that to you. It's one keyword that, at least in my experience, it generates a lot of confusion. So I will explain that later to you. What I can say right now is that this is not the element size used in calibration of the GISSMO material card. I've seen that many users have interpreted this keyword or this flag like this reference size for the material calibration, but that's not what it means. Next flag is NUMFIP, which stands for the number of failed integration points in your element before your element gets eroded. It can have a positive value. The default value is 1. So as soon as one integration point has failed, you have element erosion. But it can also have negative values, which are actually only available for shell elements. And why is that? Because, well, if it's a positive value, it's really the number of failed integration points. So let's say if you have 4 in there, it means that if 4 integration points have failed, you will have the element erosion, which, for instance, can work very well for element formulation 2 shells, where we have 5 integration points through the thickness. And then if 4 integration points have failed, then you have element erosion. And this works reasonably well for element formulation 2. But if you have element formulation 16, where you have 4 integration points per layer through the thickness, it means that if those 4 integration points in the first layer fail, then you have element erosion. This typically leads to a very, it fails a lot in your simulation. So it's better to work with a percentage of the integration points, and then you can activate this through using here negative value in front of the value here. So for instance, minus 80 means that 80% of the layers have to fail before the element is eroded. I have here one example of a tube which is actually crushed, and here on the right-hand side you can see the deleted elements in the undeformed configuration. Yeah, so here, because if you use the deformed configuration, you can't see much more. So here you can see that if I have a very low value of numfib, let's say 20% of the integration points, you have a lot of eroded elements. And if you keep increasing that value, you have less and less eroded elements. And I get from some users that sometimes they're a bit lost, especially beginners in the topic. What should they do? If you don't know what to do, so a good starting point is if you're using solids, use numfib equals to 1. It doesn't have to be like this, but it's a good starting point. And if you're using shells, that's our recommendation. If you have shells and brittle materials, use minus 40. And if you have shells and ductile materials, you can use minus 80. But it doesn't have to be like this. So in case you have been using a different value and you're happy with that, it's really giving you good matches. Don't worry about this. This is really like a starting point if you don't know what to do. Right, next to it, we have vol-frac, and vol-frac is the volume fraction required to fail before the element is really deleted. The default value is 0.5, and this is intended for high-order solids and also for IGA elements. We still don't have too much practical experience with this, so we can't tell much. Those elements are still not broadly used in the industry. I think this will grow with time, and then we can make more assertive, we can say something else about this, but right now we don't have too much experience. It's a relatively new feature, but just for you to know, that's why it's there. All right, then we go to the second line of our GISSMO keyword. We have here LS-DYNA, which is a mandatory flag, basically. If you don't have it here, you have an error termination in GISSMO. So in GISSMO, there is no default value for the failure strain. And the simplest case is when you have a curve where the failure strain is a function of the triaxiality, like in this case. But you can have also a table 2D where you have it as a function of the triaxiality and of the Lodi parameter. And in the meantime, you can even have this as a function of temperature and strain rate. Depending on your settings, you can make this as a function of the history variable. And what some people don't know is that you can even use a defined function where you can really write an analytical function to the failure strain. This can be sometimes handy if you want to, if you have a analytical function from the literature and want to try this out. Just one hint, this option is generally slower compared to when you use curves and tables. So if you have large models, I really do not recommend using this in daily production. But in order to set up your environment, I think this can be quite useful. In my talk here today, I will not concentrate on how to get to those curves. I think you will get more information about this in the next two talks from my colleagues Sergio and David, where we see an application for polymers and also application for metals using solid elements. All right, let's go to the next key flag. We have ECRIT, which is basically the instability curve. It's important to say that ECRIT is not mandatory. So if you don't want to use this, you don't have to, okay? And the default is basically 0, which means that if you don't set anything here up, what you're gonna get is that it starts to couple right from the beginning. Some users, I noticed over the years that they have this option, like just like this, they just put 0 here and 0 in decrit, and they have way too much failure, and they are a bit like lost on this because it's coupling from the beginning on, and it makes everything much more critical. Okay, so if you want to avoid this, set ECRIT to 0 and decrit to 1, then you can avoid this. But if you want to use it, I suggest you to use your negative value here. So it's an indication to the curve, for instance, or a table that you have. If you have a curve, it will be the failure strain as a function of the triaxiality, or here in the case would be actually the strain for the instability. You can also use a table 2D where you have it a function of triaxiality and of the loading parameter, and in the meantime you can even make it a function of the temperature and of the strain rate. And when that equation that I showed you before, when F is equals to 1, then you have the coupling at the beginning, right here. So that's basically being driven by this curve or the surface that you have here. I would talk on the afternoon about this, but one question that we get a lot is how to calibrate this curve. It's actually not very simple, but 2 years ago we had 2 presentations in our conference in Bamberg. I have the links here so you can take a look at this, and we kind of find out that for instability, in the sense that you have a homogeneous stress state and goes to be a heterogeneous stress state, the Swift criterion, for at least for metallic material, seems to match very, very well our simulations. So this could be also a starting point. Damage exponent. If you look at the equation of damage, you see there is this letter N here, which is the so-called damage exponent. If it's 1, which is the default value, it's a linear damage accumulation over the plastic strain. But if you set this up to be a value over or more than 1, like 2 or 3 or whatever, you get a non-linear in this sense. But this value can even be less than 1, so you get a linear accumulation, also non-linear, but in the other sense. Yeah. Strictly speaking, you should calibrate this value on experiments, but we made a few experiences with this. For instance, if you set damage exponent to be 1, 2, or 3, that's the expression, or those are the expressions that you get for those values. For instance, damage 1, it's just a simple fraction that you get in the end. For damage exponent 2, you get this one here, where you have a square root of d, and for damage exponent 3, for instance, you get the cubic root of damage to the power of 2. It turns out that computers, in general, they can calculate those 2 things here much faster than they can calculate any other root that you might have. So cubic roots or roots of the 4th order or whatever, they will be slower. So some time ago, I did this experiment where I just simulated a tensile test with different values for the damage exponent. And of course, you will get a different solution. But what's interesting is that if you use damage exponent 1 or 2, you get faster solutions, much faster. That's because of the computer, how it calculates those roots. So that's why we typically advise our customers and users to use either damage 1 and 2 if performance is an issue. If performance is not an issue, you can really calibrate this value to a very specific value, which I already have seen some customers doing this. But if performance is an issue, using 1 or 2 will give you faster calculations. And then next to it, we have decrit. Decrit, it's per default 0, but if let's say if you have 0.8, that's the equation for the reduction of the stress. So that is the material degradation that you can really have in GISSMO. So that in that sense, it will be really a real damaging. It's not always active because, as I told you before, there's always this damage variable which is available. And this damage variable, it's not necessarily affecting the stress here. So in this case, for instance, I have decrit 0.8. And when that value is reached, then you start having a coupling between stress and damage. If you want to know what is the amount that you have here, well, what is the amount which is really affecting the stresses, you have it in a history variable here. This is the effective damage value, and you can really have this in your output. If you don't want to have this behavior, as I said before, set decrit to 1 and accrit to 0. You can turn it off. Generally, we advise people to at least put let's say a high value here, at least 0.9, 0.95. I think David will talk a little bit more about this in his talk. But if you don't want to have this, you can do it, but you have to do it, all right? If you don't do it, GISSMO will begin coupling from the beginning on of your simulation. The next flag is fading exponent, and fading exponent actually you can actually regulate how you have this coupling. That's this variable m here. So if, for instance, you have here 1, you have this kind of coupling, you have 3, you have this kind of coupling. The higher this value is, the later this effect will take place. In my personal experience, values between 1 and 5, they have some influence. Above 5, they start having almost no influence in your simulation. So if you have a very high value, for instance, 100 or so, the difference in your simulations with or without coupling will be very, very small. This example that you're seeing here is for one element test. So when you have one element, you see it a little bit more, but as soon as you have something a little bit bigger, like a tensile test or a real component, this effect really almost vanishes for values above 5. And here you have a lot of options. If you have fading exponent bigger than 1, it's a fixed value. If it's less than 1, you can make it as a function of the element size, a function of the triaxiality, and even a function of the loading parameter. So you have a lot of freedom to define this value. Typically, that's our experience. Fading exponent, it decreases with increasing element size. Yeah, that's how we typically do our calibrations. Let's go to the next flag, where you have here the load curve for the regularization. Now, if you really have a tensile test, so uniaxial tension, and you do this with different mesh sizes, you will see that the strain in the critical zone, in the necking zone, will be varying. Yeah, so this is a spurious mesh dependence, as we call it. And you have the possibility to compensate for that, because if the strain is getting smaller and smaller, even without GISSMO, just MET24, for instance, it means that your failure from a global point of view, or from a structural point of view, it should take place sooner and sooner. And that's what this flag can do. So if you have just a positive value here, you will have here some factors which are have an influence in the curve. And here's a visualization of those factors. If actually those two flags here are wrong, they should be 0. But if those two flags are 0, that's the effect that you get here. This failure curve is reduced and reduced, but for all triaxialities. And actually works very well for a tensile test. If you do this, you get this kind of response. Although the plastic strain, the critical region, is really changing, you will have the same global response, which means that the energy that you're dissipating in your simulation is the same. If you don't do this, the energy that you have in the dissipation will be a different one. So that's what this flag is doing. Over the years, and that's not only coming from us, studies have shown that this regularization or the mesh dependence is not really, it's dependent actually on the stress state. For instance, if you have shear, you have no mesh dependence. If you have tension, you have a lot of mesh dependence. So actually, if you want to work with regularization, you should make it stress state dependent. But if you don't use those other flags here that I wrongly have them here, it will only scale down the whole curve for all triaxialities. And now let's get back to that ref size flag that I showed you at the beginning. And in my experience, I think this is one of the flags that makes most confusion among our users. But basically, perhaps because of the name, and I will try to explain what it does and what is the sense or what is the motivation at all to have this flag. Well, it turns out that I have here just one element under uniaxial tension. I'm just pulling it, triaxiality is 1/3. If you have 1 millimeter mesh and a 5 millimeter mesh, and your material card is already regularized, okay? So here I already have a regularization included. If you take a look at the damage over time for the 1 millimeter and then for the 5 millimeter mesh, you will see that the damage evolution is not the same, it's different. That's on purpose because we are regularizing. We want the 5 millimeter mesh, let's say, to damage faster because the failures curve is actually lower. So we want to have that. So, and this is okay. I mean, if you're just working 1 millimeter or 5 millimeters, this will work. The problem is if you first do a simulation with 1 millimeter, and then you stop your simulation, and then you want to do a second simulation where you are using 5 millimeters, and you want to map the pre-damage that you have for 1 millimeter to the 5 millimeter mesh. That's the problem, because then you have here a difference in your damage value. You have to correct this. And that's what the ref size flag does, okay? So here, I put here 5, but this 5 is intended to be used with the 1 millimeter mesh. So I first do the simulation for 1 millimeter mesh. I have the 5 here, and I have an additional history variable here, the ND plus 9. And if I look here, I'm not sure if you can see it very well, but basically this red curve here is on the top of the blue curve. And this is the simulation with 1 millimeter, but corrected to the 5 millimeter reference size that you have there, okay? So that's what this flag is doing. It's really correcting. But if you don't do a subsequent simulation, this flag will have no effect at all. I know that some customers, they put here in this flag really the reference element size that they used in the material card calibration. If you have been using this and you're not really transferring data from one mesh to the other, that's no problem about this. It's really a post-processing things. But just for you to know, that's what it's doing. What we also know is that this flag is not perfect. When you really want to map from one mesh to the other, it's not a simple process. So that's why we have, in the meantime, a negative ref size, which actually provides you a better estimation. For instance, if you have very high damage or if you have non-proportional loading. But even this option, it still has some limitations because this problem is not easy. All right, so I will go back now to the line where I was, and now we have the inst F flag, which was something that we requested a few years back. I have to say this flag only makes sense when you're really fine-tuning your model. It's really, it's when something just is not perfectly there, so you want to use this. There are some options here. I will not go through all of them, but basically it makes sense. I noticed this when, for instance, I was calibrating one material where we wanted to use an instability curve, a grit curve, which was very low, but the failure curve for this material had to be very high because it was localizing a lot. And I noticed that for the tensile test, in order to get a good correlation, I had to use a fading exponent of 2. But in order to get a good correlation for the notch tensile test, I needed to have a fading exponent of 5. If I had 5 for both of them, it didn't work. If I had 2 for both of them, it didn't work. So the only way to have both of them is really using this inst F flag. where I can set up my fading exponent to be a function of the stress state. And also, especially here in this case, it worked best when I said that once the instability is reached, the fading exponent is kept constant. So that's where it's coming from, so that you know. But again, this is really fine-tuning of your model. This doesn't make a huge difference later in your component simulations, for instance. Then I have LC soft, which is there, and this flag is actually related to the soft flag, which is in the next line. So that's why I'm having both of them here. And just the soft flag is a factor that you can use to reduce the failure curve in the neighborhood of an element which has been eroded. Yeah. So for instance, if you put here 0.5, it means as soon as one element has been eroded, the elements in its vicinity will really have half of the value of the failure curve. It turns out that if you just make it just like this, sometimes you have some problems in components, so you really need to make this as a function of the triaxiality and even of the element size if you want to be more accurate, and that's why we have the LC soft flag, which is here. That's what I use in this example. I just have here a tensile test, and I just said that the soft factor for low triaxialities is 1, but for higher triaxialities it will be 0.1, which means like really reducing drastically the failure curve for high triaxialities. And that's the effect that you can see. Until then, to the point that you don't have failure, both results are exactly the same. But as soon as you have here the first element eroded, you can see here that when I'm using this lower soft flag, the crack propagation, it's much, much faster. So in a nutshell, you can say that this soft flag, or the LC soft flag, helps you to control the crack propagation with even with element erosion in LS-DYNA. And I know that some customers are already using this productively. They are really using this now in their processes. We're coming to the third line, where we have the LCSRS, where we have the strain rate dependence through scaling factors. This can be just a scaling factor of the hardening curve, of the failure curve, as a function of the strain rate. You can also define this as a triaxiality dependent factor solution, but I think in the meantime, it's easier probably just to use the table 4G that you have here in LC-SDG. Yeah, so we use this sometimes, especially for plastics, because plastics are very strain rate dependent regarding failure. Just pay attention. This is something that I saw quite a few times from customers, that they run a simulation, they have a curve like this, and then suddenly you have a failure at the first time step. They start a simulation, they already have failure, and it's looking very bad. It's typically because you have here an extrapolation of this curve like this. So if one element somewhere has a very high strain rate just for a second, sometimes it really has a failure strain of 0, and that's why it's fading just immediately. So be careful with extrapolation of this curve at the last point. One recommendation is just to use a horizontal line here, so you calibrated your material up to that point, and from that point on, for instance, you can consider this to be a horizontal line so that you don't have this problem. You can do this also here for lower strain rates. I have here one example of a PC ABS by my colleague Sergio. Will be showing a little bit more about this just after my talk. Then we have shear factor, BX factor. I have here one example, 1 is 0. Well, if you don't have shear factor and BX factor, that's what happens with the regularization. It really reduces the whole curve for all triaxialities, but we know that this is actually a very harsh criterion, because for triaxiality 0, when we have shear, you shouldn't have any mesh dependence. So if you set shear factor to 1, basically you have full regularization for triaxiality 1/3, where we have uniaxial tension, but we have no regularization for shear, for instance. And if you set these values, both values to be 1, then you have no regularization under shear, no regularization under biaxial stress states, triaxiality 2/3. If you want to read a little bit more about this, you can take a look at those 2 papers that I'm referencing here. If you don't know where to start, I always suggest a good starting point is setting the shear factor to 1, because this is quite clear. You should have no regularization at all under shear. And since I'm talking about regularization, these are 2 new flags that came up last year, I think, where basically, if you look here, I will go back 1 slide. If you look here, you can either, from triaxiality 1/3 to 2/3, you can either have full regularization for all the triaxialities, or you have a linear interpolation between triaxiality 1/3 and 2/3. But we noticed that this is also not really satisfying, so that's why we introduced these 2 flags, where you can say that the full regularization is happening between those 2 triaxialities that you can put here. So here I have one example that between 1/3 and 0.577 triaxiality that corresponds to a plane strain stress state. You have the full regularization, and from those point on, you really have the linear interpolation until you have no regularization at all. If you're interested in this, last year I held a presentation in our conference in the United States about this. Here's the link to these slides, so you can also take a look at this if you're interested in this. Now I have the LS-DYNA flag, which is actually a curve. Originally, this was thought to be used under compressive loadings. Okay, so that was a request from a customer saying, okay, under compressive loadings, I don't want to have failure. I want the material stiffness to reduce, but at some point, I don't want to have any failure, any element erosion. But at the same time, I got some questions from some users. They said, I want to have the damage stress coupling, but I don't want to have the element eroded. How is that possible? And that's why I generated this example here, where first you have just the default setting, no LS-DYNA, but here with some LS-DYNA, where I set for high triaxialities, I put the limit of damage to be 0.9. Which means that you do have the coupling and everything, but when you come to damage 0.9, the element stays there and it doesn't damage any further. I personally never use this flag in a practical application, but if you need this kind of a feature, it's already there in GISSMO and you can use it. Then we have mid-fail, which is also a flag that was introduced a few years back. And it comes back to the fact that actually when we use GISSMO, everything lives, so to speak, or is calculated in each integration point. But some users had a different opinion, saying that, for instance, things like instability, this should be for the whole shell element. Yeah. So this option is only valid actually for shell elements. And basically, it translates anything about instability to the middle surface of the shell. I've never used this option really in practical applications, but I tried a few times to understand it, and at least so far, my conclusion is that if you use the different options, you get very similar results to the fact when you use like mid-fail 0, which means there are differences. If you look here at the undeformed configuration, you see that the number of failed elements are not the same, but I cannot tell you which is better, which is worse. But I don't know. I know that some customers are using this option, and perhaps in some special cases, it might make a difference. So just for you to know, there's also this option in GISSMO. We have his VN. I don't want to spend much time here because my colleague Cristoph Wilking will be talking more about this. This is interesting when you have like a mapping from a manufacturing process simulation, but I will just leave him to talk more about this in the afternoon. And finally, we have our final flag here, LP2BI. This idea is basically coming from MET 258, and that material model has a failure model embedded to it, and it has what we call the bending indicator. This bending indicator, denoted by this letter here, omega, you can see here the omega, it's really like a bending indicator. If it's 0, it means that in your element you have a pure membrane loading. If it's 1, you have a pure bending loading. And if it's somewhere between, you have a combined membrane bending loading. And comes from the idea that failure should be treated differently if you have bending or if you have a membrane loading. So this was a request from a few users, a few customers that we have to use this. And I tried this feature as well. I tried to understand a little bit better. By the way, if you set here this to 1, it will activate its usage, and then you need to set up your LS-DYNA not as a curve, but as a table. And this table is no longer a function of the loading parameter, but it's a function of the bending indicator. So this has to be from 0 to 1. And here you can define whatever you want. You have to calibrate this, of course. And you also have the option where you have LP to BI equals to 2, which means like it's just like the first option. There's just one difference. There's no regularization. There's full bending. There's full regularization. You have membrane loading and a linear interpolation between those two states. So when this came out, I was talking with one of our customers, and he said, well, let's try this out. Let's see how it works. And we tried this for a homogeneous material through the thickness. It was a sheet metal. And basically what we did was, that we set up so that the membrane curve or the bending curve is a function of the membrane curve through a factor. So this factor here can be changed, but the dependency on the triaxiality is the same. So here we have no bending indicator, so the classical case, and then we have different values for numFip. And in order to get this resolution here, I set up the number of integration points of the shell to be 10. So we have really a nice resolution of numFip. And it turns out that if you change that factor here, you almost can find a correlation between numFip and between this usage of the bending indicator. And by the way, when you use the bending indicator feature, you have to set numFip to 1. Otherwise, it doesn't really work well. Okay, so at the end, we came out with the idea that if you use this or that, you will get similar results. At least in this case, we also tested this for a bending. It had a similar result to that one. I think one advantage perhaps of the bending indicator is that here I had to, when using numFip, I had to increase the number of integration points. But for the bending indicator, you don't have to do this. It's, let's say, a little bit less dependent on the number of integration points that you have through the thickness. All right, now I really showed you each keyword or each flag that we have in GISSMO. You can see it's quite a lot. But again, remember that the problem that we want to really resolve here is a complicated problem, this failure problem. But one question that I also get when people are beginning this, okay, you have a lot of flags, but which ones are the most important ones? And I flag them here. These are, in my experience, the most important ones. LS-DYNA, so this is your failure curve. This is the most important one, right? So you really have a big influence in your simulations depending what you put in there. But another one which has a big influence is numFip. I have seen some cases where users actually have a very good failure curve, everything is in place, but when they simulate their components, they have a lot of failure because they didn't set numFip, they just have 1. So that's the example that I have here below. So numFip 1, you can see here, it's failing a lot, but if your material is rather ductile, actually you should change this value, okay? So sometimes users really have good cards, it's just the numFip flag is missing. And finally, when you have regularization, I've seen this quite a few times that people don't set any stress state dependent regularization. So if you set shear factor to 1, it can also increase your or improve your results quite a lot. So I think those two flags are are also very important. The other ones, they are also important some way, but of course, in comparison to those flags that I highlighted here, they are, let's say, more fine-tuning when it comes to the damage simulation. And now I'm coming to my final slide. I get sometimes this question, what is the next implementation in GISSMO? What is going on? And I would just like to highlight 3 tendencies that we see in the industry so that you know about this. I see a lot of usage of solid elements, not only for parts like this wheel where it's obvious that you need solid elements to really get it geometrically accurately described, but sometimes even for parts that you actually can mesh with shells. But shells also have limitations, and sometimes, and it's increasing, I'm seeing people using, let's go for solids, let's have it a little bit more accurate. So it's one tendency that we see in the industry. The second tendency, quite clear, is mapping things from manufacturing processes like forming analysis, but also die casting simulations and so on. It's quite clear that people are using this. And finally, this is also quite a trend. Stochastic analysis. You have the variation of material properties, and most customers or many customers are using like a min, mid, max approach. So you have like the worst case, the best case, the mean case. But I see some customers using a more sophisticated way to treat this in a really statistic way. So this is really beginning to happen. One customer at least told me, well, I had min, and it was not the worst case in my simulation. The worst case was somewhere else because it's complex, it's very nonlinear. And although I didn't show you here today, you also have an option to use a stochastic analysis with GISSMO, okay? So I just want to mention this. These are 3 tendencies that we are seeing in the industry right now. Thank you very much. And if you have any questions, I will be glad to answer them.
Thank you, Filipe. I want to apologize. We had some issues with the quality in the online stream. People here didn't notice, but I'm sorry. I mean, we're going to switch the network now. But anyway, are there any questions from the people here on site? So no questions? Something you want to know? I mean, he's an expert on GISSMO. Ask him anything. He will know. Okay, yeah, there's one. Yeah.
It's possible to count it with solid elements right now, but it's not possible.
GISSMO?
Yes.
Yeah. It's
Okay, so just for the online audience.
You can use solid elements, perhaps if the audience online didn't hear.
Yeah.
It's possible to use it with solids, no problem, yeah.
Does the same come with solid and shell?
I'm sorry?
The same come with shell and solid?
That's a very good question. The question is if you can use the same material card for shells and solids. I'm going to answer this question in the afternoon for the frequently asked questions. It's we get almost every day this question.
Okay, another guess for a good question. Okay.
Do you know about usage for beams?
Okay, the question was how to use GISSMO for beams. It's implemented for at least one beam time that I don't remember right now. But beams are also limited in the description of the triaxiality. So there are some limitations, but it's implemented. We got this request a few years back, and it's working. But remember, beams are really like an idealization of a real structure. So you have limitations in the description of the stress state, and failure is very dependent on the stress state. So long story short, it works, but it has limitations.
Okay, there's another one.
We always talk about greater strain. Is it a total strain or plastic strain? Does it depend on the material model?
Okay, the question is about the strain that we use for the failure. In the general or in the simple case, in GISSMO, you have the plastic true strain, the plastic equivalent true strain, but you can change that if you want. Oh, sorry.
For an unfit equal to 1, the criteria for failing, is it that each integration point must fulfill the criteria or only one?
I will go back to that slide. Yeah. The question was if numFip equals to 1, it has to fulfill all the integration points have to reach damage 1 or just 1. It's just 1, okay? So if you look, for instance, in MAT24, if you use the fail flag, all integration points must reach that criterion before the elements get deleted. But here, numFip 1, it means a single integration point. So in that case here, if you have here 20 integration points. If the first one has failed, the element gets eroded. And typically, you have a lot of failure in your simulation.
There's another.
I wanted to ask a follow-up question for this one. If we have materials with nearly no plastic strain, like for example CFK materials, do we switch to just a strain formulation, or do we switch it to a more brittle formulation?
It's a good question. Let me just go back here. Do we have some time still, Mike?
Yeah.
To the original idea of GISSMO. Let me see if this video works now. Because the original idea was really to describe this, right? So you have a lot of plastic deformation. So you have composites like carbon fiber or so, you almost have no plastic deformation, right? But some people are still trying to use GISSMO anyway in that sense. I think I even referenced that example that we have a customer working with airbags, but he's so used to working with GISSMO that he said, I want to work with that also with airbags, and airbags are not really plastically deforming. So it's important that if you select a variable for this damage accumulation, I have it here, that this variable at least does not get negative. Otherwise, you have negative damage increments. You can even get negative damage, and that's not the purpose. But using GISSMO for extremely brittle materials with almost no plastic strain, it's still a little bit challenging. Yeah, but that was not the initial idea of GISSMO. Yeah.
Okay. I mean, there was also a question online, but I think we already ended it. His question online was if it's also feasible for solids, and you said yes already.
Yes,
yeah, so
it's feasible for solids.
Okay, I think we stop here. We move on to the next one. I think there are also here more questions, there are also online more questions, but if you have more questions, if you're here, feel free to reach out to Filipe in the break between. If you're online, feel free to contact us. We're also happy to answer the questions there. Okay, so thank you, Filipe, again. Okay, next speaker is my colleague Sergio. He's from Madrid. He did his master in Madrid. He also did his PhD in Madrid. He had a couple of visiting stays. One was in Swansea, if I'm not mistaken, also the Karlsruhe Institute of Technology. And in 2016, he joined DYNAmore. And since then, he's also working on the GISSMO. So let me just start his presentation. Okay, so here's your presenter, Sergio. You ready?
Yep.
Okay.
Thank you very much.
Sergio, the stage is yours.
Thank you, Mike. Thank you very much for the nice introduction. I come originally from Seville. I studied mechanical engineer in Seville, and then I moved to Madrid to do my PhD. And today I will be talking about obtaining a triaxiality-dependent failure curve for polymers, just using tensile tests. Sorry. I don't know how it works. Yeah, the pointer is where? The top. Okay.
Wait, you can use the mouse. Not the pointer. You just press it.
Okay, it's working. Thank you. Yeah, as I said, the topic today will be obtaining a triaxiality-dependent failure curve for polymer just using tensile test. First of all, I would like to talk about what we name what behind polymers. So when we talk about polymer, we are talking about plastics material that have typically chains, which could be intricate in the material. We know they can exhibit anisotropic behavior. They are generally non-isochoric, or when they plastify, this plasticity is non-isochoric. And we also know that damage can be triggered by deviatory or also hydrostatic contribution. And when they undergo loading, we typically observe such stress strain curve, where we have typically a peak and then a softening, flat evolution, and at the end they experience a hardening. That's the goal of our modeling today, or we would like to model this behavior. For the failure, we would like to use GISSMO, as I will show later. Typically we make this distinction, or we classify the polymer, or first of all, we will be focusing on thermoplastics in this work, and thermoplastic could be classified in these two groups. Unreinforced plastic, where we typically have ductile behavior with this so-called telescope effect. They can be considered isotropic, and they often exhibit a huge strain rate dependence. Yeah? As I said, they are usually non-isochoric. And on the other hand, we have these reinforced plastics, typically with fiber, where we have pretty much brittle behavior with no telescope effect, and with a highly anisotropic. We distinguish, or the stiffness is quite different when we test it in one direction or on another. As the unreinforced, they could be strain dependent, so they often are a strain rate dependent, and also non-isochoric. The tool we have in LS-DYNA to face the modeling of such polymers, I have here in this slide. When we face the modeling of ductile behavior, for instance, we can make use of MAT24, the standard, plus GISSMO. But as I said, we know the plasticity here is non-isochoric. That could lead us to use the MAT187 or L, plus the GISSMO. GISSMO is intended for anisotropic failure, or for considering an anisotropic failure. As I said, that is if we want to capture the transversal behavior that we observe in polymers that are typically non-isochoric. On the other hand, for the reinforced plastics, we can use MAT24, but we know that we have the limitation that we cannot cover every response that we get according to the orientation, because it's an isotropic material model. But we still use it because it's easy to use, and we have a lot of experience on it. What we typically do is to have two material cards, one for one direction, one for another direction, and so we can cover this anisotropy. Or if we want to just use one material card that covers all the behavior for every orientation, we could go for MAT157, where we can model in the anisotropy in the elastic regime and in the plastic regime. For the failure, we can resource to GISSMO to distinguish the failure according to the orientation. Okay, that is the tool we have in LS-DYNA, and we use it. And then I bring here a little bit of motivation, because when we want to model failure for plastic, and when we want to use GISSMOs for that, we typically need to do different experiments for the characterization of different stress states. But we try that. We perform, for instance, shear test or node specimen test. The problem we found out is that due to the deformation process of polymers, of plastic, we ended up with not the desired stress state, but something near to the stress state of tensile test, so triaxiality 1/3. That means we have a lack of information when describing this failure curve for the whole range of the triaxiality. We try to do compression tests, but normally the compression tests are tricky because we can have backlimb. As I said, the other tests weren't good enough, so we thought about, okay, we could do bending tests. They are easy to perform, and as well easy to be modeled by a finite element model. And we thought how we can make the most of this bending test to define our failure curve. We know by bending we don't have homogeneous stress state. We have rather variation of the stress state through the thickness, where we have compression in the outermost fiber, tension in the opposite side here. But we observe is that the bending test, also when we tested polymers and the bending, we usually get rupture in the tensile area of the bending. And that gave us an intuition that this curve should look like this, as should looks lower in this area of triaxiality, and higher in the compressive part of the curve. As I said, we went in this way, and we needed to define a curve, or to have a method to define a curve that we can test with only tensile tests. Using bending tests, we could validate our proposed method. That was the idea behind this. The question was how we can do that. Yeah? And then we came up with this idea. It was quite old, this Koch-Latham energy criterion, which is an energy criterion where we define the energy as an integral of the first principal stress, for the positive values of the first principal stress through the plastic strain. And it says, or it predicts the failure whenever this energy reaches a critical value, WC. The problem was, okay, we don't know much about this, how this WC should look like. And but what we do have is the tensile test, and there we can measure the failure strength. And we came up with the idea to use this failure strength that we measure at tensile test to estimate this critical value, so that we don't have any more energy parameter to be calibrated, but we can, from the experiment, we can extract the information from the tensile experiment that we have. And that is what I'm going to show in the next slide, how we can build a failure curve for GISSMO, for triaxiality-dependent failure curves, based on this criterion and using the information that we have in tensile test. So for that, I need to to show a little bit theory, but it's not that complex. I think we can define a general stress state or a general plane stress state like that. In terms of the first principal stress and a parameter K. Given that, we can define the pressure and the equivalent stress. And with them both, we build the so-called triaxiality, and we have a relationship between the triaxiality on this parameter K. And as I said, we need to perform the integral, we need to define the first principal stress, and we can do that if we assume, in this case, von Mises plasticity, where we know that the equivalent stress should be equal to the hardening curve. And considering that, we can define our first principal stress like that, which is a function of the hardening stress and the K parameter that we have introduced for defining a general stress state. It is worth mentioning that for K equals 0, or the first principal step is the first principal state, stress state equals the hardening curve, defines what we have in the tensile test. So it defines triaxiality 1/3. Okay, as I said, we have such an expression, and now we can solve for this integral, or perform the integral. As I said, we need the critical WT value to define the failure. We need to, that is important, we need to solve this integral for each K parameter. We need to vary this K parameter so that we can define different stress states. For each fixed stress state, K, we can find the failure strain that define the failure for such stress state. When we do that, we need a hardening curve, as I say. Here I show a typical hardening curve for a non-reinforced polymer. with this curve, I do the integral, and I obtain a curve like this blue one. Yeah? And on the other hand, we have the variation of the triaxiality in terms of, as a function of k. And within them both, I can define the failure curve that we want. When we combine it, maybe I go back. When we combine those two curves, we obtain the desired failure curve here. That looks like this. It predicts no failure for compression and beyond, for negative triaxiality or lower triaxiality as a minus 1/3, and has this quality feature where we can identify that it predicts the same failure strength for tensile, triaxiality 1/3, and biaxial tensile, triaxiality 2/3. And the minimum shows up by plane strain. Here I show on the left hand side how this curve looks like for a hardening curve, for a typical hardening curve for unreinforced polymers. But here I have as well the same curve, but when we use a flow curve that is intended for reinforced polymers. We don't observe a difference or quality difference. The only that changes is the values of the failure strength for different triaxiality, but we still have the same prediction for of failure for tensile and biaxial tensile, and we still have the minimum there. Here I studied a little bit the influence of the failure strength, because we don't have to forget the input. We just need one input for the generation of the score. On the input is a failure strength that we can measure in the tensile test. What's happened if we change this failure strength, this input, we have here 0.79. There I change it to 0.13, and that is what we observe. Yeah? We get a much flatter curve in the area of triaxiality 1/3 and triaxiality 2/3. That is the influence. We cannot change the form of the curve. The form of the curve is given by the Crocus-Layton criterion. Okay. Then another important thing when we want to modulate failure with GISSMO is, in the case of polymers, is to consider this strength rate dependency that Filipe mentioned. This slide was to warn about that we need to cap this curve, yeah? As Filipe said, yeah? That we typically need it in order to have a good curve. On the other hand, I would like to point out here that we typically observe such evolution of the strength rate at break, although we also observe pretty much of a scattering of the strength at break for polymer. But as an average, we expect this behavior, and that means that this curve should looks like decreasing, or should decrease, yeah? with higher strength rate. Okay. Another topic was, as I said, we usually need for the modeling of plastic or it is not sufficient to model it with von Mises plasticity with MAT24, but we need to go for a much richer model. In this case, can be the Dagger-Prager modeling, and we wonder if this approach work when we use Dagger-Prager modeling. That is what I'm going to show in the next slides. Or the answer was yes, it is working. We can use this approach. The only thing we have to consider is that now we have an influence of the pressure, and we have two hardening. We have typically two hardening curves, one for tensile and one for compression, for the compression response, and this formula becomes a little bit more difficult, but in the end we can go with it and build a failure curve. Here is an example how we can implement this Dagger-Prager modeling using MATSEM or MATSEM Lite, where we can input two hardening curve, one from tensile, one from compression, and we can define plastic boson ratio as well if we need it. With them both, we can have this modeling. In order to be consistent, when we use this modeling and we want to model the failure with GISSMO, as I said, in order to be consistent, we need to adapt this approach to this case, and that's what I did here. As before, I have the generalized stress states in terms of a parameter K. Now the first principal stress looks like this, where we have the influence of the hardening curve for tension, hardening curve for compression, and the integral we need to solve seems like this. And again, we need to estimate WC for the failure. Again, for the case of K equals 0, we end up with first stress state equals the tensile hardening curve. Okay. When we perform this integral, we obtain such a failure curve, which doesn't have the same quality feature as before, because it predicts the different failure for 1/3 and for 2/3, and the minimum didn't show up by plane strain. But in a general sense, we have also the similar form. The influence it isn't that much. Here I used for the compressive hardening curve the same as in tensile, for the tensile, but with a factor A. And I did the same. I checked for what happened with unreinforced plastic and reinforced plastics. Okay, as I said, that could be in order to be consistent when we modeling with a Dagger-Prager modeling. Here I have an example where I apply this idea, this approach for real material, PCABS, that was presented back in 2018 from my college, Martin Helbis and Andre Heufer. And we we had a tensile test, quasi-static and dynamic. For the quasi-static tensile test, we had DIC recordings. Yeah, the specimen has this dimension. For the same material, we performed a bending test, as I said, because we wanted to use bending tests to validate this approach. We performed bending tests, statics and dynamics. On the dynamics one, we were performed by the pendulum of the 4A company, and we obtained such a result, some test result. That is the stress strain rate, stress strain curve for the quasi-static tensile test, where we identify the typical behavior of polymer with a peak, a softening, a plateau, and a hardening. I show here how the strain field looks like for the different stages that we observe in this behavior. I did a calibration, in this case based on the MAT24, with strain rate dependence, where we use log interpolation as a detail. And I normally work with a 5 hardening curve to have a good description of this strain rate dependency. That is quite important when modeling polymers, because we observe when we don't have a good description of the strain rate, we have difficulty in modeling the failure. We need to calibrate where strain rate factors, so to speak. As I said, I did my calibration. I obtained a good agreement for every strain rate that we tasted. As I said, it's important to have such a good description in this in plastics regime in order to have a good modeling of the failure. The same, I simulate the bending specimens. I obtain such an agreement where we were quite satisfied. Maybe we can observe here a lack of stiffness, but we can live with that. That was everything without failure. And then we went for failure, and we calibrate this GISSMO card. In this case, it wasn't that difficult because we only needed to define a failure curve based on our introduced approach, Koch oscillation, and the strain rate factors, the LCSRS curve that Filipe mentioned. And with that, here I use this value from the experiment. That was the input for generating this curve. And you may have to iterate a little bit there in order to capture the right failure strain, because we did the assumption that we constant 1/3 triaxiality, but we know in the real work in testing we don't have a constant triaxiality, and that's why we need to iterate a little bit. But according to our experience, we don't need too many iterations. Yeah? We can get a good agreement with 2 or 3 iterations. Here I show the result with failure for tensile and bending. And the good point was that we get a good agreement here in the tensile test while we don't have failure in the bendings as we observed in the experiments. So we can say we have made our calibration based on tensile tests. We obtained this failure curve based on that. Here, everything looks like good. But when we validate with our bending test, we observe a good correlation as well. So we were happy with what we obtained with the approach we introduced. To end up with, I show some details of some evaluation of the simulation versus experiments, where we don't only have a good agreement in the global response stress and strain, but also a good agreement in the strain fields at different straining. Yeah? And not only that, but also we had a good agreement through the time. Although our goal was to have a good agreement here in the stress strain space, we also obtain a good agreement through the time. Here I show for other strain rates how it looks like. And as I said, we were quite happy with the approach and with the modeling. We could use Mathlib and GISSMO based on this idea for Koch data. As concluding remarks, I have said everything, I think, but we can use this crocodile idea or this approach to calibrate a failures curve that delivers a good result for tensile while not damaging the bending. Doing like this, we avoid the so far widely used state form of this curve, but before we introduce this curve, we usually observe that the customer had a fixed value for the compressive part of the curve and another fixed value for the tensile part of the curve. So with that, we can build a continuous evolution of this curve. The results are promising, as I said. We can face out the strain rate dependence that we observe for polymers. As a further work, we would like to validate this calibration at a component level. Unfortunately, we don't. We are expecting to have the opportunity in the near future. So I finished my presentation.
Thank you, Sergio. Okay, we're a little bit over, but still, I think, are there any quick questions? I mean, something online. If you still have time, just post it. Are there any questions from the audience here on site? Okay. If not, I have a quick one. At the end, you showed this ABS material, and they have the typical this plateau. You go like have a peak, and then you have a plateau, and then going up again. Was not clear to me. The plateau, is it like a damage thing, or is it part of the material model?
It's a part of the material model.
It's not a damage.
It's described by the plastic behavior.
It's okay. It's part of this one. Okay. Something else. Someone wants something. Okay, so we're anyway over time, so I move on to next speaker. Thanks again, Sergio.
You're welcome.
And the next speaker is, of course, again, a colleague of mine and even a former colleague. We have been at the University of Stuttgart at the Institute of Applied Mechanics. So David studied civil engineering, then did his PhD, working on civil engineering topic, geothermal plants, actually. And now he's he's leading the group and the testing in the lab. And he's talking about the material characterization, working with solid elements. So let me just switch the slide to David's. Okay, David, you ready?
Yes,
okay,
I
so
think
the stage is yours.
Maybe I have to change the pointer.
Oh, yeah, you have this one. Okay.
Yeah, thanks a lot. Yeah, I want to welcome you all here to GISSMO Info Day, here on site and also online. I think it was a very good idea to make this happen, this Info Day, because there's so much interest in this topic. So yeah, I want to talk a little bit about material characterization for GISSMO simulations when it comes to solid elements. There was already this question before. Yes, of course, you can use GISSMO for solid elements, and I will show a little bit about this. So this somehow the content. I will start to talk a little bit about DYNAmore's Material Competence Center, where we do material calibrations. I will talk a little bit more general about testing, why we need testing, and so on. Then we will see the 3D stress state. What kind of specimen geometries do we need, or do we at least have? And then a little bit about the input for the GISSMO model for solids, what's important and what needs to be considered. And I will finish with a small example. So I think this could all be the position here, the location where right now. So it's near to Stuttgart, in the middle of Europe. We are here in southern Germany, and the lab, the Material Competence Center, is not here in Vaihingen, where we are right now, here near to the airport in Leiden-Echterdingen. On the right, you can see the current team of the Material Competence Center. But we are growing, so there will be another colleague starting in June. This is some of the equipment that we have. So we just, I think 2 years ago now, we bought this water jet cutter to just be able to really quick extract samples from metal sheets. And we have 2 of these DIC systems from size, and for these measurements, we have to apply a spec pattern on these specimens, and therefore we have this kind of a UV LED printer to apply this pattern and follow all the points on this specimen during the test. Then we have 2 testing machines. So universal testing machines. We can do quasi-static tests with this machine. We can do tensile compression and bending. For some materials, they are quite sensitive to temperature and also to humidity. And for these materials, we have this climate chamber. It's a small climate chamber, but it's really important if you have materials like PA or also some foams and all this kind of stuff. You need to have a specific temperature and a specific humidity also within the specimen when you test it. Then for some dynamic tests, we can use a pendulum. We can do dynamic bending of polymers, and we can do compression tests on foams up to a certain strain rate. Of course, it's limited somehow to its size. And then we have some tests that we do really often, like the small tensile tests and some shear tests. So all the tests, not all the tests, but many tests that we need for material characterization when it comes to sheet metal. And we set up an automated procedure. So we have a robot that actually is doing the work here for us. So it picks up the sample and it presents the sample to I'm not sure if it can be seen right now, but there's some 3D scanner. So it's a GOM, and we afterwards have really a 3D model of the actual sample, and we can do the measurement all on this model. Then the robot places the specimen in the tensile machine, and after the test, it removes also the leftovers. And yeah, this whole process is completely automated, so there's no human interaction needed. So you can just put, I don't know, 20, 40, 80, how many tests you want to have. You can place it and start a robot and he will do the work. So testing. Why do we even need testing, right? So we are all in this simulation world, but somehow we are always in this kind of a model world also. But there's also this world. It's the reality, and we have to bridge the gaps somehow. And this is where testing comes into place, right? This is where reality comes into our models. So when we look in reality, what are the reasons for materials to behave like they behave? So we have some molecular properties and configurations. We have interaction of chemical elements within alloys, for example. We have a structure on mesoscale, like we have in metals. We often see this grain size. So the grain size is also an influence on the material behavior. And of course, we have something like a treatment during manufacturing of some components. And when we go to the model world, we can, at least at now, we cannot consider atomic properties in our full crash car model, right? So we have to use models. We have to make assumptions. So we have a modeling approach and assumptions. For example, we can assume that our material behaves like in the von Mises plasticity, right? Or we can state that we have a homogeneous material, or the material is independent on temperature. So these are all assumptions that we add to our models. Of course, we have material parameters, and these material parameters we get from testing. They depend on the model, and of course also on the results from the real world testing. And we have some initial conditions. We already saw in the talk of Filipe, this idea of having several steps, for example, starting with a forming simulation and then mapping the results onto a crash mesh. So what we are doing is we have the physical test, and we also do a simulation of these tests. So we have the same boundary conditions, same dimensions, everything's the same. And then we have the results here from testing, and we can extract the same results from the simulation. And then we compare these two, and we optimize the parameters until we get quite good agreement between the simulation and the reality. And then I thought of what kind of data can we even get from a test? So we can measure the force. So there are force load cells. We can get the force in terms of a diagram, force over time usually. Then we can use something like this tactile extensometer. So we have at 2 points, we measure the displacement. We know the length scale between these two measurements, so we can calculate something like the engineering strain. So we have the force and the engineering strain over time. But we in our simulation world, we are used to have much more information, right? So you can get information from any point in your simulation. You can get the stress, and you can get the strain and temperature and whatever, every parameter that you have that you want to have, you can get it in your simulation. But in the real world, it's not possible to measure all of these values. So we have force, and we could use this type of an tensile extensometer, but we could also use the IC. The IC gives us much more information. So with the IC, we can really get a displacement field of the whole surface of the specimen during the whole testing procedure. Right, so you can see it on the right. We have this is the major strain. It's just derived from this displacement field, right? Yeah, and now we have this data, and we can do whatever we want here. We can apply an extensometer and get equivalent values as we have it here from the tactile extensometer. But we can also look here close. So what are the highest values of strain we have here? So it's 120% here, for example, right? So this is crucial information sometimes that we only get when we use DIC. So let's talk a little bit about stress states. So we already learned today, probably not before, that for solid elements we do not only have the dependency on the triaxiality, but also on the loading parameter. So we have this area here, and the triaxiality actually, it goes from minus infinity to plus infinity. So every number is allowed here. The loading parameter is restricted to values from -1 to 1. And these two values can fully describe the stress state of a point. And this means now that if we want to define the failure strain depending on these, on every stress state, then we have to define the failure strain depending on these two variables, the triaxiality and the loading parameter. I added another curve here. So this is actually the plane stress curve. So whenever we use shell elements, we are directly somewhere on this curve. No other values are allowed, only the values on this curve. So you see, we have for every triaxiality, we only have one loading parameter. So there's a direct relation. And we can reduce, for shell elements, the number of dependent variables, and we can only use the triaxiality and define just a curve instead of a surface. And you also can see that the triaxiality is restricted to values from -2/3 to 2/3 for the shells, but of course not for the solids. Okay, so now we have to think about, so we know that we in a simulation we could have any possible stress state, but we need to find some failure values, some failure strains for all these stress states. So we have to think about what kind of element, or what kind of specimens, what kind of tests do we have to make. So we have flat tension tests. These might also be notched, and we would end up probably somewhere within this area. We could do round tensile tests, also maybe notched. And we would end up here with a loaded angle of about 1. And we could also do plane strain tests, where we also have notches in the specimen, but not from the width, let's say, but from the thickness side. And yeah, we could do Nakashima tests or punch tests. We would end up down here somewhere. We could do shear tests. Shear tests are in this region here. And depending on how brittle our material is, when we have a very brittle material, we would probably get values down here. If we have a more ductile material, we could end up somewhere up here. And there's another example. It's a butterfly specimen. Depending on the geometry and on the boundary conditions of this specimen, we could get values from somewhere within this area. Of course, there are other specimen geometries and other tests out there, but this is roughly the information or the area that we can cover. So we still see that there are large areas where we almost have no test available. Yeah, and moreover, the butterfly, so this test and the plane strain specimen, they're quite challenging to manufacture and also to discretize with finite element method. If you don't want to go too much into detail, yeah, if you're restricted in element size and if you can't use too small elements, then it's quite difficult to mesh these kind of geometries with a constant mesh size. So obviously we need to do come up with some assumptions for these big wide areas here. Okay, so let's talk a little bit about the input for GISSMO for solids. We already saw this. Filipe showed us some values. I will focus on some values that are important for solids. NumFib, we already heard about this. So these are the number of integration points that needs to fail until the element gets eroded. Default is 1, and default is also, I would say, a good starting point to use it when it comes to solid elements. You should always keep in mind that the L form, so that the type of the element that you're using, could heavily influence how the results are that you get. Because if you have an element with just a few integration points, it may completely different when you have an element with a lot integration points. When you, for example, use a NumFib of, let's say, 4, right? So this could be all of the integration points, or it could be just 10% of the integration points, so just some rough numbers. Yeah, so it might be a huge difference. So just changing the element type could also really influence the result. And yeah, so there's this coupling between NumFib and the L form. Then decrit. For solids, we usually use decrits, but we almost always we don't need any strong coupling here. So we usually want to use, we would like to use ecrit with 0 and decrit with 1. In this case, we would not have any coupling, but if we decrease here the value a little bit, this could lead to an increase of stability within the simulation. But because if you don't have any coupling, it might be that you have a sudden failure of an element, and this could induce some kind of pressure wave or some waves that propagate through your component. And if you just decrease this value a little bit to 0.95, this is just some number. It could also be 0.98 or just a value here that it's not really sudden deletion of the element but there's more or less a fade out of the stress and not a sudden rupture. So this could be done to increase the stability. And then we have, of course, the failure surface that we have to define. It's now a 2D table. So I tried to come up with a sketch on the right side. And on the left side, it's an input example. So we have to define a table 2D. We have the table ID. And then we have curves for several loaded parameters. So these are just 5 curves. Usually we use more than 5. So it really depends, right? And yeah. We have for every loaded parameter here, we have a curve defined. And of course, we need to define the curve afterwards. And in the curve, we have the failure strain depending on the triaxiality. So some comments and recommendations maybe. We have limited information because we cannot do tests for every stress state, right? So we have to come up with some assumptions, and this assumption could be that we don't have any dependency on the loaded parameter. So we end up just with a curve, and this, yeah. We can also, in this case, we could also just apply a curve ID within this position in the input. And Filipe mentioned a similar problem when you look at the scaling factors for strain rate, and also we have the almost same situation here, that we usually want to have a decreasing failure surface for increasing triaxiality, but we only define this failure surface up to a certain value, right? So from this point on, we need to make sure that the extrapolation never crosses the axis, and it should because the failure strain should never get less than 0. So also in this case, we would suggest to just add a little horizontal edge on this failure. And yeah, what we often do is we set a quite high value, but we set a high value also for compression. This could also increase numerical stability, because if you have really high deformed elements, you may end up with some negative Jacobian or something like this. But yeah, these are really high numbers. Usually we use a number of 5, for example. So we have really a true strain of 5 when it comes to failure under compression. Then I also brought a small example. It's from a research project, KI-LAST. It's founded by the German Federal Ministry for Economic Affairs and Climate Action. And yeah, these are all the partners that work with us on this project. And the goal of this project is to support the design process of additively manufactured lattice structures with artificial intelligence. And of course, also here we need, as a base, we need a reliable and a robust material model and according characterization. So these are the geometries that we used for the characterization here. So we have different tensile tests. We have the classic uniaxial tensile test. We have the shear test, some other shear tests with a different loading. We have a notch tensile test. We have a punch test. We have a bending test. And then we have 2 round tensile tests notched with different diameters in the notch. And at last we have a compression test. I don't want to go through all these results here. Just here with a uniaxial tensile test, you see the colored curves are the tests, and the black curve is the calibrated curve from the simulation. And on the right, you see this is this stress state area, right? You have the triaxiality and the loaded parameter, and this is the strain path of the first 5 elements that fail during simulation here. And It's actually not one strain path, so it's 5, but they're too close to each other, so it just looks like one. Yeah, and because it can't be seen that good here on this picture, we also have it here in 2 diagrams. We have the triaxiality and the equivalent plastic strain here, and as you can see, as we suggest, we have at the beginning a triaxiality of about 1/3. And when it comes to necking, which is at this point, the triaxiality increases a little bit, and we have failure. The loading parameter is almost constant at 1. A completely different picture is when we look at this punch test. So again, we have the tests and we have the simulation. Here we see it's a more conservative approach for the simulation. We have, okay. Yeah, and on the right, you can see we have really strong nonlinear behavior in the strain path. And if we look from these 2 directions, we see that the triaxiality, as we expect, it's about 0.6 or a little bit higher, so 2/3 about. And the loading parameter, there's a big change here, but it ends up at a value of -1. But you can see it's highly nonlinear. So, and we do not only have this nonlinearity for the punch test, but also for other tests. And there's a crossing of these strain paths and so on. So we need to solve this problem in a coupled way. So we have a strong coupling, and we cannot fit the curve on a certain point and then go the next step and fit the next point. So it needs to be somehow solved coupled. So we need to run the simulation for almost every test and get the results and then adjust the failure curve accordingly. But it influences each other. So and this is the failure curve that we came up with here for this research project. You see we have this high plateau for the compression, and here we have a failure surface that gives us good results for the tests. Here, just for visual reasons, there's this dark line here. This is the line of plane stress. So I come to the summary. Okay, a little bit over time. So at the MCC, we provide material characterization. So if you need help or just let us know if you need to have a material characterized. I showed that I think that testing is crucial to bridge the gap between the model and reality. I showed that how the stress state depends on triaxiality and loading parameter. Different tests are necessary to capture all this information to calibrate the failure surface, but still some assumptions need to be made because we cannot do tests on every stress state. And finally, I showed that the strain paths are generally nonlinear, and this needs to be kept in mind because you cannot just derive a value for the failure surface from a single test at this stress state. And maybe a final take-home message: no fear of solid elements. Maybe just give it a try.
Okay, thank you, David. We have time for questions. I mean, afterwards we have a longer break, so we still over time, but we have time for questions. Are there any questions from the audience on site? Anything? Okay, yes. Yeah.
Thank you for your presentation. Question that you define the failure strain based on, for example, the simulation and the test. So you take the failure strain only at the point of its triaxiality and the failure strain value, or do you make any calculations because sometimes the triaxiality or load angle is not like linear during the load. So you only take the point of the failure and take this value of failure strain, or do you make any calculation for this nonlinear case?
Yeah. So the question was, if I if we just take this value up here where we have a triaxiality of 0.7 and a loaded parameter of -1, and just measure this value here for failure. No, because as you said, we have this nonlinear behavior and we are accumulating damage over time here. We have an increasing equivalent plastic strain. So we are doing the simulation, and we do not just enter a value there, but we are optimizing the values that we're using for the failure surface according to the results that we get from the simulation. So it's not just a one way, but it's an iteration to optimize these values.
Okay, and in that case, you mean like you collect the information and you use optimization way to get the failure stream value in that case, because there are so many parameters in the GISSMO model. So will you also change other parameters, or you only optimize the failure stream value during the optimization? Yeah,
so the question was if we just optimize the failure surface or also the other parameters. So it depends. For some materials, we have values that we know that work quite well. For other parameters, for example, the damage exponent that Filipe showed earlier, we for the most cases, we just use a value of 2, so there's no optimization there. But for other values, there is some modifications needed. Maybe we see that with a certain configuration of parameters, we cannot find a good agreement for many tests at the same time. So in that case, we have to go back and change other parameters and then come back to the failure surface. But as you already mentioned, there's so many parameters, and you cannot optimize all the parameters at the same time.
Okay. Thanks. And in that case, because you are using solid elements, if I want to apply the result from solid elements to shell elements, for example, is that also possible? Because sometimes the solid elements are just within the thickness direction, and it doesn't cover all the triaxiality of the thickness direction. So if I want to apply the results for shell elements, do I need to make any modifications for that?
It depends. So the question was if you can just take the material card that you have calibrated for solid elements and use it for shell elements. Yeah. So to some extent, this is possible, but I would always recommend to at least do simulated tests on different stress states and see if the results from a shell simulation is the same. Yeah. And if you have real tests or test results, then try to match these.
Okay, so I want to add some questions from the online audience. There are a couple of them. I'm not sure if we can cover all of them, but for the online audience, if you have a question and we cannot answer them, feel free to contact the speakers directly. It's always firstname.lastname@ansys.com. Yeah. Anyway, so there's one from Aaron Lopez, and he was asking, how do you measure the cross-section during the experiments when the tensile tests?
The cross-section. So we measure the cross-section at the beginning before we do the testing. Yeah, with the this is the wrong one. So, for example, with the robot does this. Oh, too many here. So on this sector, we have a real 3D model, and we can do the cross-section measurement before we do the test. But also during the test, we can do some measurements because we have this information from the DIC, right? So we do not only have the strain in longitudinal direction, but also in transverse direction. So this is we could also somehow, calculate we can calculate this value also during the test to some extent, with some assumptions, of course, because we only see the surface with the DIC. This is also important to know.
Okay, thank you. There was another, is an online audio, like an on-site question? Then I can, okay, on-site again, okay.
So sometimes we need different GISSMO definitions for solids and shells. So that means that we have injection molded parts, or we have thin parts, and very thick parts, which you model with measure with solids. Then we should use at least two material parts. Or we have to calibrate two material parts.
So I'm not sure if I understood the question correct. So you have two parts or two areas within a component. One is quite thick, and you need to use solids, and for the other part, you want to use shell elements. Okay. Yeah, I think this is basically the question goes in the same direction as before. So you can use a card for both, but I think it's a good idea to at least do some virtual tests if you get the same results for the same boundary conditions. So some tensile tests, some shear tests, maybe a punch test.
Maybe my question was if it just comes to no fit and the other parameters are the same, then you need to have two cards. Maybe we can have
Yeah. If you have numfib equals 1 because you need this for the solids, of course you probably have to adjust this if you go to a shells. Yeah. You could do this by simulating tests, for example, and see what kind of a numfib do you need for the shells to get the same result as you get for the solids. Assuming that your material card for the solid is good, predictable for this test.
Okay, so I add another online question. Well, yeah.
Just a short.
Okay, then on site. Okay.
Because if it's about the numfib, as I understood, for solids it's always 1. So if I use a GISSMO card which has like -80, for example, and I use it on solids, it will be automatically 1, right?
I'm not sure. -80 will probably change it to 1. Yeah, it does. Thanks. So if you have -80 and you use it for solids, then it's 1. It's used as 1 within LS-DYNA. But don't need to have 1 in solids. You could also use 2, 3, 4, and so on. So of course, depending also somehow on how many integration points you have. And then at this point, you get the coupling to what kind of element type you choose.
Okay, then add another one from online, from OMCAM. So if you have defined a load curve and a critical plastic strain in E-grid, will D-grid be still considered?
No, E-grid is over D-grid. So if E-grid is defined, then D-grid is ignored.
Okay, good. Okay, and there's another one from Onye. He's asking how to approach time step problem with small solid elements. Are there any recommendations on mass scaling, so continuous mass scaling, selective mass scaling? Are there any?
Yeah, so this is not really specific to GISSMO. So it really depends. If you have just some small elements, use selective mass scaling, and yeah.
Okay, and the last online question, and then we make the break, from Alexander Pabst. How do you obtain the failure strain curve for different loaded parameters?
Yeah, so as I said, you have to make some assumptions because you just have information for some areas, right? And there are closed functions out there that are used, for example, with Spiky by or something like this. You could use this. You can do some other assumptions that maybe you have you have a linear interpolation between a curve that you have, for example, at loaded parameter 0 and one at loaded parameter -1. So it's difficult. So this is probably the point where you could think of Occam's razor. So this is the idea that you cut off any assumption that is not needed to explain the phenomenon. So if you don't have any values, maybe it wouldn't be a good idea to add some hills in this area, right? So you don't have any assumption, to just maybe go with a smooth interpolation.
Okay, so last one question from on-site. If there's not any, then okay. So last one, and then okay.
I'm working a lot with adaptive remeshing. On the previous presentation, we had this deep dive into this reference length topic. Is this relevant for adaptive remeshing with solids? Because I'm starting with a very coarse mesh and then I get very small mesh sizes. I think somehow this is coupled to this dimension topic.
So the question was if this ref size flag could also be used or is considered when doing remeshing during your simulation. And as far as I know, this is not the case. So I think that the damage values are just used for the new elements also.
Okay.
So this is could be improved in future maybe. Yeah, but at the moment this is not the case.
Okay.
I have a following comment on that. I'm sorry, but I'm not sure about the reference size because in the first slides, in the first presentation, you said like the reference size is relevant to the model you are using for simulation, not the one you retrieve the information. Is that correct?
So, for example, you do the forming simulation with the element size of 0.5 millimeters. And you use this, or in this simulation, you use a ref size value of 3. Then all this information that you need for the crash simulation later on is also saved with for a mesh size of 3. So you can use this and map it to this new crash mesh that has an element size of 3.
Okay, so if my model has within 5 millimeters, it's not a 5.
Yeah. So you can, yeah. So it is only important. This value is only important for the next simulation.
Thanks.
Okay. So we're done now. Okay, so we have officially a break now, and we continue at 1:30, which is, if you're a different time zone for online guys. Then based on your local time, you compute when we continue, but it's 1:30 Central European summertime. Okay, so see you in 69 minutes. Okay, see you. Okay. Okay, so welcome back, everyone. Welcome back on site. I think you're not feel so stuffed. I'm pretty full actually after the lunch. Also, welcome back for the people online. And we continue with our program. And the next speaker is Cristoph Wilking. He's my colleague from Ansys. He's also kind of former colleague. He also studied at the University of Stuttgart civil engineering, did his PhD, but at a different institute. But now we're working together again at a DYNAmore / Ansys company. And he will talk about bake effects in aluminium using GISSMO. Okay, so please, stage is yours.
Thank you very much, Mike, and welcome everyone to this talk. The topic is considering paint bake effects on aluminium sheets with MUT 251 and GISSMO. So today we want to share our experience we gained regarding the combination of this MUT 251 and GISSMO. And with we, I mean Filipe and myself, together with Markus Voigt from Mercedes, where we gained all those experience. As mentioned earlier today, I will talk about a GISSMO feature which can be activated by giving here this variable which is called his VN, so history variable number, and setting this variable to a negative number tells LS-DYNA to evaluate the 3D table of this LC-SDG and the 3D table of this eCrit, and to use the history variable for that. So we get a failure strain and a critical strain, which is now a function of this arbitrary history variable we can set. And well, the standard loader parameter we heard of, and the triaxiality. With Mercedes, we started to use this GISSMO feature and pushed the development of this feature because we wanted to improve the accuracy and the predictability of the aluminium material cards we are using for crash simulations. With this feature, we are now able to account for the influences of the manufacturing process in more detail. So, to understand what is the physical meaning of the history variable we are using here, we should have a closer look at the manufacturing process of a car. So, let's start with this one. So, of course, it's not all steps of the car manufacturing process, but yeah, just some major steps which are important for this talk today. So, at the beginning, we have here an aluminium sheet, which comes in this delivery state, this most of the time called T4, so it's not pre-treated. And then we form our part out of this sheet. After that, it's all put together, all those parts are put together, and there's this painting coming onto the car, and the car later on goes into this paint bake oven, and well, it's heated up for 20 minutes for more or less 180 degrees. And well, we will call this process route here the standard T4. And here are some properties of this route related to the other routes we will see in a second. So here the formability is quite good for this material, and the costs are compared to the others good as well. But here it's not temperature, this temperature stability is not that good, because here in this process the material properties might change depending on how much heat is going to our aluminum. So, and we have another process which is similar in the first state. So we get this coil here in this T4. Then we form our part out of this sheet But after that, this part goes into an additional oven and is post. So there's the heat treatment before this one here. This is usually 30 minutes for over 200 degrees. And after that, those parts are put together with the other parts. And again, the whole body in white goes into this paint bake oven. So this, we can call this one here like this one here. We see here compared to this process route, the properties. So the formability is of course the same because up to here, everything is the same. But the costs is more costly because we have an additional step. We have this oven here, where we have to put all our parts in, or those parts we treat like this. But due to this oven here, nothing or almost nothing changes in the material properties, so its temperature stability is better compared to this T4 route. And then there's a third route I want to consider here in this talk. It's T61. So those coils here are pre-treated with heat, and after that they are formed into the final geometry, and they don't need to go into this oven here, but they can just be assembled to the body in white and go to this paint bake oven. So in this route, compared to the other, here the formability is not that good because we have a pre-treated material here, so we can't create fancy geometries with that one, but we have temperature stability, but here the costs are much higher due to this pre-treatment here. So now let's look at the two major steps here in this process which can change our material properties. So this forming and this paint bake process. So first of all, let's look at the forming process. This is a simulation we will see here. So just a simple simulation. And we see that during this forming process, we have here plastic strains in our part. So, and now those plastic strains, of course, they can affect the material properties of our aluminum. So if we want to test this and see the effect, we can perform some tensile tests like this one here and just pre-strain those tests. So for example, here with 6%, 12, 18%, and then perform those tests and put that all together in this engineering strain diagram. And we see here, if we have no pre-strain, we get this answer, and we get other response with higher ultimate strengths and higher yield stresses for the pre-strained tensile tests. So this effect here is called work hardening, so that we get higher ultimate strengths here, for example. And we see here in reality, at each point of our part, we have different material properties. So maybe here we don't have pre-strain at all, so here this behaves like this curve, but other points like those one here, the red parts, they behave more or less like this. Okay, so that's the forming simulation. Now let's have a look at this paint bake process. So here is, with this video, it's an illustration made from a simulation. So we are here inside this oven with a body in white. This body in white goes through this oven, it heats up, so it gets hotter and hotter in there. And now we can see that the heat is not homogeneous in the whole body in white. We can have a closer look here, just to one part of the simulation. That's this door here. And if we start the simulation, we see how it heats up, and we see that each point of our part has a different temperature profile. So here if you look at this point here, we have a temperature profile like this, so it's more or less constant over the entire time of our oven process. But here, this part or this point is covered by the outer sheet, so it doesn't heat up that fast, and the profile is a little bit different here. So how does this affect our material properties? So we can again perform some tensile tests, and now we before we test our specimens, we heat them up, for example here 180 degrees for 30 minutes or 120 minutes and so on and so forth. And we see that here we have a similar effect as for the work hardening. And this one is called precipitation hardening or bake hardening. Okay, so we see that our material properties, they depend on the temperature profile we have in our parts. So that's really, it's a curve. In order to get a scalar value, which more or less has all the information of the curve inside, we could use something which I call here degree of precipitation. This degree of precipitation can have values between 0 and 1. So 0 would be unexposed, so this T4 delivery condition, and 1 would mean it's fully precipitated, it's a T6 condition. We can get an estimation of this degree of precipitation by, for example, this Johnson-Mel-Avrami-Kolmogorov equation stated here. And then we get for each temperature profile, we get something like a curve like this. That's a degree of precipitation, this red curve. And at the end, we get a final value. And this one is here, something like 0.42 or something. And we can map this information onto our crash mesh, and we can end up with something like this. So at each point, we have one scalar value, this degree of precipitation, which more or less represents our temperature profile. For the mapping, we could use, or we use in this case, Envio. It's also a tool that's developed here from Ansys, from us. We could use this in order to get from the temperature profile and with the information from this equation here, from this JMAT equation, this degree of precipitation. Okay, we can then do that for each integration point. So each integration point or each point of our door has a different profile. We get different degrees of precipitation. And so we could somehow consider this bake hardening effect. Okay, let's go on to the material characterization. First of all, we will have a look at steels, how we can consider those two effects, so work hardening and bake hardening in steels. So normally, and that's what my colleagues showed here a couple of years ago at an LS-DYNA conference, what we do normally, we have a material card. That's we obtain it by this T4 condition, and then we somehow consider this work hardening and bake hardening just by going here into this hardening curve, and then just put here some this pre-strain and an additional strain coming from the work hardening. So we have here the assumption that we consider bake hardening as work hardening, and put this information here just to this initial stress shell cards as a pre-strain of our material point. And with this approach, we can see here, we have good accordance with for the experiment in black and the simulation in red. For 0 pre-strain, if we add more pre-strain and also those bake hardening effects, we see if we consider both, so this red curve again, we have a good accordance for all our test results here. So how does it look like if we adopt this to aluminum alloys? So we here have the same approach. So we're using one material card with only one hardening curve, so MUT 24, and this initial stress shell cards for each integration point. So we have good accordance here for 0 pre-strain. If we look at 5% pre-strain, we see it's not that good anymore, and it's getting even worse if we have more pre-strain in our tensile tests. So that's what we typically see if we have aluminum alloys of this 6000 series. So usually it doesn't work with MUT 24 and initial stress shell, so not the same way as for most of the steels. But we could use this MUT 251, which is also called MUT Taylor properties. So let's have a closer look at this material model. So it is very similar to MUT 24. Here in this MUT 251, this plastic behavior is a function of, and that's different to MUT 24, 2 history variables. And then the strain rate and plastic strain S for MUT 24. So what can those 2 history variables be? Here are 2 examples. That's what we use here in this process chain. It can be a pre-strain or, for example, this degree of precipitation. So we can have actually several hardening curves, more or less. So it's for each pre-strain we have tests for. How does this material model look like in an LS-DYNA input deck? So that's how it looks like here. And well, here you state where LS-DYNA should look for this history variable you're using here as to state this plastic behavior. So here it's again given this MUT Taylor properties, and well, we have then here a 4D table in order to prescribe our plastic behavior. And here I tell LS-DYNA, okay, look at position 6 of the history variables, and then LS-DYNA checks, okay, I have here a 4D table, so I have to look at position 7 first, so 6 plus 1. And here, that's what we have as a user have to do. So we have to put here this degree of precipitation, and then here the pre-strain. So LS-DYNA looks first at the degree of precipitation here in this 4D table, and then, well, it's the next table in the 3D table, it's a pre-strain, for example. But that's really up to you how you put your tables together. Well, and then comes the strain rate. Here it's not strain rate dependent, so we have the same curve IDs here. And here, finally, comes one hardening curve. And this one hardening curve is then here for a degree of precipitation 0, pre-strain 0, and strain rate whatever. It's not dependent. And then we have here the yield, the plastic strain. Okay, that's how MUT 251 works, more or less. And if we use well, go back one slide back here. Well, what really we have to do is we have to put this initial stress shell information, so all our pre-strain information and our degree of precipitation to all integration points. We will do that by this initial stress shell cards. And that's what you normally do before you're performing your crash simulation. So you map your information from the forming simulation and the paint bake simulation, for example, with NVO to a file of which just describes one part. And in here are, well, the node and element information, and also those initial stress shell cards, like this one here. And then you can use, for example, this include stem part to map those informations from just this one file, this one part, to your whole car body or your whole car mesh. And well, in here, in this include stem part, you have the possibilities to state something like material or model type here. And you can put, for example, if you're using MAT 251, you can put 251 here. And then LS-DYNA looks if the part where he tries to map those informations to has really this material type. And if it doesn't have this, there's an error termination, and you know that something is wrong. And that's more or less just to avoid that you unattendedly map some history variables to somewhere where other information should go to your material models. So that's just to avoid some mistakes by unattendedly changing your material model in the car, in the full car model, for example. Okay, so that's MAT 251, and we get all the information there. And now we can perform our material characterization for the aluminum, and we see that we have good accordance with the experiment. So we now have really for all our tested pre-strains, a different hardening curve, and we match the experiments quite good here. But so far we haven't considered failure. So that's what we want to do now, and therefore we are of course using GISSMO. And well, I already told you that in the first slide, that in GISSMO we have this feature here, HISVN, which actually works in a similar fashion as this MAT 251. So here you have an additional history variable you can use in order to describe your failure strain and your critical strain. And this one is again totally up to you what you put there. We use here in this process chain, we are using either a pre-strain or a degree of precipitation. So a difference here compared to MAT 251, you only have one history variable you can use here. But so far, it seems to be enough, at least what we saw in our testings. So let's have a closer look at this at the keywords. So if you state here -6, LS-DYNA will look at this position here of your history variable and takes this value in order to evaluate this 3D table of, for example, your failure curve surface and your instability curves. So you could come up with a material card which has different failure curves and different instability curves depending on your, for example, pre-strain or degree of precipitation. Okay, so let's go to the aluminums, and well, we considered more or less 3 levels or four levels of material characterization. So level 0 would be, so you don't consider any pre-strain or oven simulation at all. Level 1 would be no manufacturing simulations, so you just consider like average values for the pre-strain and for the degree of precipitation. So if you know, most of my material points will have like 5% of pre-strain or this KTL ideal temperature profile, then well, you can just use those values and do your characterization for this for the state. And level, well, we call it level 2 here, where you consider one manufacturing process. So either forming simulation or paint bank simulation, and you're using the averaged quantity for the other values for the other quantity. And with level 3 is the most complicated one, it's the most detailed one. So you use here really the actual values from your simulation at each integration point, and for each all of those pre-strain and degree of precipitation. So of course you have increasing accuracy going to the right, but of course also increasing complexity. So let's have a look at this complexity again. So for material testing, what do I need to what tests do I need to perform to get a material card like this, so MAT 251 and this GISSMO with his VN variable. So level 0 would be just, you don't consider at all this degree of precipitation nor the pre-strain, so you have to perform a full GISSMO calibration here at this point, more or less. Level 1 would be you perform this full GISSMO calibration at this point here, so average values for degree of precipitation and pre-strain. And now level 2, you could say, okay, I consider average value for the pre-strain, but I want to have this degree of precipitation and look at this one in more detail. So you can decide where you want to use this full GISSMO calibration, or just if maybe just tensile tests at some points are enough for you. It's really up to you and depends on the accuracy you want to have from this material card. Or you can do a level 2 like this one here. And then level 3, you see, you need a lot of testing. You need a lot of tensile test and full GISSMO calibration, and this it gives you probably the best material card, but of course it's very expensive to perform all those tests, and it takes a lot of time to come up with this testing and to come up with the material card. So here it's probably the budget that will not allow you to do that. And maybe it's not even necessary, because we, at least for this 6000 aluminum, we have quite good experience with this level 2 approach. So just testing one of those rows. And here we want to give one example of material characterization we did a couple of months or weeks ago. It's 6000 aluminum, and we already had a material card of this level 0 type. So this looks like this card here compared to the experiments. It's fully regularized here, what we see here. And then we want to add material card of this level 2 with MAT 251. So that's MAT 24 here, and now we want to have this MAT 251 in combination with GISSMO, and we did some additional testings here, so just tensile tests. So we took all the information from GISSMO, actually from this one here, or we started with this GISSMO cards here. We performed this tensile tests. We pre-strained the sheets. We took the specimens from 0 to 4 and 8% pre-strain, and heat treatment of all specimens for 180 degrees for 20 minutes. So that's more or less our testing scope here. And all those tests were performed at the MCC of David Koch. And here are the results of the testing of the tensile tests. So for all those pre-strains here, and we took those informations here to get hardening curves for each pre-strain for our MAT 251, and those instabilities curves as well for our GISSMO card. And then we started to have this failure curve from this MAT 24, and then we compare those results to the experiments, and we get quite good accordance here in all our states. And of course, we can also test like other pre-strains like 6%, and they match quite good with if we have performed other material testing for this as well. Okay, so that's what we did here. We also did some regularization. We had a new material card, so we had to do that. So there are the results without regularization. So we have here this 0 pre-strain tensile tests, and we performed this one with different element sizes. And so without regularization, it looks like this. So then we did our regularization and we came up with something like this here. And now we want to check if this regularization also works for the other pre-strains, so for 4 and 8%. And we see here it works not perfectly, so it doesn't work look like this, but it's quite good, I would say. So and we see here, since we took the same regularization because there's no option in GISSMO so far that you can give your regularization in terms of as a history variable, we still have quite good results here, and it's not necessary to have this dependency here in this case. Okay, so to conclude my talk, I presented you this combination of MAT 251 and GISSMO. They both work in a similar fashion, so if you understand MAT 251, it's quite easy to use this GISSMO as well. It's very flexible. You just have this one history variable you're using, or those two, and you can put whatever you want there, So for our use case, it was this pre-strain and the post-precipitation hardening, but you could put whatever you want to. And this here you have the yield stress and the material failure is then dependent on those arbitrary quantities. You have to map the information before your crash simulation to your crash mesh. And here it's again stated MAT 251 has 2 history variables. GISSMO is so far only 1, but from our side we have good experience that this is here enough to get good results and better material cards. If you want to use all those features here and you want to make sure they're working properly, I would suggest you to use, for example, an R12.2.1 or an R14.1. Okay, that's it. Thank you very much.
Thank you. Okay, first on-site audience, do you have any questions, comments, feedback? Okay, maybe I have a more or less stupid one, I'm not sure. You showed these different levels of simulations, what you have to do, like just simple, including manufacturing, including bake effects. And you also showed this depending on the precipitation level. Are there some kind of general guidelines when to use what, or how did you came up with this?
With this one here?
Yeah, exactly. Yeah. Is it very special for this application, or is it more like something you can do general?
I think it's special to this application, but what to choose, it probably depends on the accuracy you need for your simulation. If you're fine with this one here, level 1, so it's probably faster to use this one here, but you're probably not as accurate. So if you're really looking into details and looking into some cracks that might propagate or some come up, then it might be good with level 2, or maybe you even need level 3. Yeah.
So basically it's more like based on the experience and kind of like trial and error. And
probably the budget available, because it's very expensive to perform all those tests.
Money. Okay. Okay. Some comments. I mean, we're actually already over time. There's one, Markus.
One comment. The level 1, of course, is the first step, is the first choice when you start with the simulation. And then, for example, the heat open simulation helps you. Perhaps in some cases you have a quite homogeneous. If you have a quite homogeneous temperature curve or a load curve over the time, and you have a homogeneous situation, then of course you don't need to account for the details. And this is often the reason you get the experience when you have first open simulations, and then the people can tell you, okay, here might be a problem, you do not have enough heat, and so the decision is mostly then taken by the experiences of the open simulation.
Okay.
Similar is it for the bay carving for the paint base. I mean, Christoph, you showed that when you a similar problem with steels. Steels have quite nice linear behavior. So, and therefore, we don't probably not need to switch to 251. And this is kind of general, let's say, experience or recommendations for steels. You can describe the bay hardening good enough because the material behaves quite linear, and so you don't need to switch to the more complicated 251. And but aluminum alloys, especially 6000 alloys, they mostly need the more exact description because there you have yielding behavior.
Okay, so just to summarize the answer, basically it's depending on the nonlinearity of your material behavior, kind of like how homogeneous you have the distribution and how not homogeneous you have it. It's like how local you have the changes in the material properties, whether you go with a full or simplified version. Okay. Okay, one question from the audience here.
I'm just curious what kind of amount of work it has to be to perform a baking simulation. Because is it just like temperature, or is it even with radiation, convection, and do I have to do a whole CFD simulation? I mean, what is the amount of work?
I'm not an expert in that, but it's not that easy, I guess. So of course you have to consider convection and all that stuff, and we have to. Well, here you see. I don't want to start this video again, but you see here the positions where this heat comes into the oven, and that also it has an influence on the parts, how they are heated up. Yeah. So it's not trivial. Yeah, yeah.
Okay, so thank you again, Christoph.
Yeah.
Our next talk is given by Harika. Thanks. Yeah. And Harika unfortunately couldn't make it because she had some issues with her visa. But anyway, we will have a video for her. So we have now a video talk given by her. So that means we cannot answer questions here, but for people who are attending online, if you have questions, post them in the chat. Harika will try to answer the questions in the chat. Yeah. So for the people who are here having questions, approach me and we forward it, or approach Harika directly afterwards. Okay. Maybe just me to introduce Harika before. She did a PhD in Cambridge. She was also for a while assistant professor at the Coventry University in the UK. She's actually also located in the UK right now. And right now she's a lead R&D engineer at Ansys and working mainly for GRANTA material database. So basically he's one of the lead developers in this field at Ansys. Yeah. Okay, now we're switching now to the video.
For crash applications. So, good morning, good afternoon, guten Tag. My name is Harika. I am from the Ansys GRANTA team. We provide material data solutions and software solutions for engineering enterprises. So today I'm excited to talk about our latest offering in simulation space, the GISSMO data for crash applications. So this follows a recent successful collaboration with the DYNAmore MCC, and we have introduced this data for the first time in one of our key simulation products called MI Pro. To those who are unfamiliar with GRANTA, I will provide a quick summary of what we are, what we make, and who we are. Then I will introduce you to three of our products which cater to simulation users. This area has been a key focus for us for the past 5 years, and it will remain a priority given the recent opportunities we have with the resources and expertise of LS-DYNA and DYNAmore teams, as well as the potential offered by new data-driven approaches like machine learning. In the end, of course, there is no substitute for physical testing, which provides the definitive truth. So we are equally committed to partnering with testing solutions to sort of supplement our databases with rich experimental data and accurate simulation data. So I will come back to this in a few slides and expand on this a bit more. And finally, the main theme for today, I will share some details of the recent collaboration between DYNAmore and GRANTA MI, the materials we have introduced, GISSMO data for MI Pro, and how this data is presented, and then close with some concluding remarks. So GRANTA MI is the materials information management system that enables the users of an engineering enterprise to effectively manage their materials data. Within an organization, usually there are data providers in, say, testing and research, and there are data consumers in, say, simulation and design. So the MI system is that one-stop location where all the proprietary material intelligence can be accessed by all users. So there are tools to control and manage this data and to ensure that it's always traceable to its source. It's also integrated with a wide range of product lifecycle management, CAD, and CAE solutions. So these are basically our key products. The enterprise solution I just described is aptly called MI Enterprise. MI Pro is a fast start version of MI Enterprise, mainly for design and simulations. And Selector, it offers powerful tools for material selection analysis. And finally, MDS, it supports the Ansys simulation analyst. So in addition to the software itself, central to any product is the materials data that each of these products is packaged with. So there is the core materials data, and there are a number of optional add-on data bundles for various applications and industries. So for every customer of every size, we have a solution. The data products team, which I belong to, is the team behind all the materials data in GRANTA. So we are based in Cambridge, UK, and a number of our colleagues are remotely based across Europe. We are a team of material engineers, analysts, and scientists. We also possess specialized domain expertise that enables us to take control of both data and strategic planning within that particular domain. So we do maintain close interactions with other Ansys teams through collaborations and feedback to mainly ensure that our strategies remain current. All right, so let's now look at some of the key products that cater to simulation users. We have 3 main products. Advanced data bundles in GRANTA MI, materials data for simulation, and MI Pro. I will introduce them briefly. So the first is the advanced data bundles. So these are available in MI Enterprise as well as Selector. There are 10 data bundles to choose from, depending on the material type and applications of interest. Data in the bundles is gathered from more than 20 reference databases containing high-quality industry-standard material data that is generated from rigorous testing program. Additionally, the MI software, it enables you to sort of browse and search data, and that data can then be assigned directly to the parts within a CAD or CAE system to perform the simulation. GRANTA Selector additionally comes with a powerful set of tools to also enable you to choose a right material for your application. MI Pro is an easy-to-install, fast-start version of the enterprise solution with just as much as is needed for simulations. So MI Pro makes it easy to build a materials database that combines your in-house proprietary data with the data we provide in the core database of 4,000 plus materials and some add-ons, optional add-ons for aerospace and electromagnetic applications. Additionally, it comes integrated with the material calibration app, currently capable of fitting material model parameters for a wide variety of hyperelastic and viscoelastic models, as well as some metal plasticity models. The fitted parameters can be exported from MatCal, and they can be stored in the MI database, MI Pro database for later use. Finally, the material data for simulation, or MDS for short, is the one that benefits users of Ansys flagship simulation tools. So it is fully integrated in that the users can find the data they need and instantly apply them without leaving the Ansys mechanical or electronics desktop interface. The MDS library contains over 2,500 materials, around 800 of which are generic materials of all types, and the remaining are producer-grade materials. So we offer simulation data for a wide range of properties, mechanical, thermal, electrical, magnetic, to basically support a typical Ansys simulation. So our current focus at Granta is towards extending this capability to some of the more advanced simulation cases, the scope of which is very wide, even if you think of one single class of materials, say metals, for example. So as such, we have to prioritize the use cases based on user requirement, as well as availability of industry standard test data. There are a number of simulation use cases we are currently developing materials data for, mainly for metals and polymers, such as conventional metal plasticity, polymer creep, and viscoelasticity, as well as fatigue and fatigue crack growth in metals, more recently sheet metal forming, and the latest, which is crashworthiness. There are also a number of ways in which we continue to make our products more ready to be consumed in simulations. The approach we take depends on availability of data and on the priority of the use case. So one approach we commonly take is to synthesize relevant data from various databases where we are contractually permitted to do so. Of course, this requires that we have the data for the exact or similar grade material across multiple sources. And then we internally develop the calibration procedure to transform the test data to simulation data. The procedure and the data are then rigorously validated by subject matter experts across Ansys before any of this data gets incorporated into a product. So we've taken this approach recently with metals forming to assemble a complete data set for Barlat models. So we combined high quality test data for flow curves in one of our databases with raw FLD diagrams or data for FLD diagrams from another, and developed estimates for the yield parameters for few forming grade steels. This data serves as typical rather than for a specific grade, but these should allow users to perform exploratory simulations of basic forming process as a first step. Through the export functionality within MI Pro, this data can then be readily exported to LS-DYNA material decks and can be plugged into a simulation straight away. So I'm not covering now in detail in the interest of time, but we now have a system of converting the engineering test data to flow curves for simulations for various types of polymers. One that accounts for the shape of the stress strain curve and in turn the nature of necking in polymers. This process has been applied to over 13,000 curves in the global polymers database, which is part of our polymers data bundle. And it will allow users to conduct more practical simulations of polymers. So another approach is to procure targeted simulation data directly from data providers. This is a curated data set and highly vetted for its accuracy and suitability for key simulation use cases. We would incorporate this data straight into the databases and develop exporters for a suite of simulation software. So along these lines, one of our recent additions has been the high temperature alloys data database. This is a data set licensed from GE Gas Power and is a result of several decades of test programs. It contains temperature dependent data for over 70 alloys used in heavy duty gas turbine manufacture. There's a wide range of property data that can be exported to select simulation software. And currently we are hoping to expand the export capability to LS-DYNA as well in the near future. In the absence of any data within our existing sources or available to procure, we generate our own data either through in-house testing or via external testing solutions. So in most cases, this means that we would develop the test program and the calibration procedure internally and have it validated by experts across Ansys every step of the way. So this approach is undoubtedly the costliest in terms of time, effort, and money. However, it allows us to produce and own high-quality test data. So we took this approach a few releases ago to generate simulation data for polymer viscoelasticity. We have an in-house testing labs in Maryland in the US who generated the test data required for extracting the Throny series parameters for shear relaxation. We developed the test program and the calibration procedure internally, and the data became available to users just the previous release. So the initial phase was fairly long in this case, especially as it involved a lot of R&D. But we expect the future phases to be more rapid, and we plan to keep testing more polymers over time. So that was a summary of our simulation efforts so far, the three main ways in which we improve our simulation readiness until we met DYNAmore. So just as we were looking to expand our simulation readiness into crashworthiness, we secured an excellent deal through a new collaboration between DYNAmore and GRANTA, one in which DYNAmore procures materials and conducts the testing required for generating material data for crash simulations. They also apply their state-of-the-art calibration procedure to generate the LS-DYNA material decks for rate-dependent plasticity and GISSMO models. On GRANTA's part, we import the data from these calibrated decks into an MI product, in this case, MI Pro, and develop exporters for users to export this data from the datasheets to LS-DYNA. Several key people from different teams have come together to successfully execute this project within a brief period of less than 6 months. So these include the technical team at DYNAmore, Andre, Christian, Timo, and Vincent, few of us from the GRANTA team, Roger from product management, and several ACE team members who provided valuable feedback on data and schema within a short time. So in this first phase, we have introduced crash data for 3 automotive grade steels, 2 dual phase and 1 complex. You may be familiar with these grade names. I will show an example of one such datasheet in MI Pro. The other 2 look similar. So all the relevant attributes for crash are placed under a separate heading called crashworthiness. We have the rate-dependent plastic flow curves ranging from 1e minus 4 per second to 1000 per second as calibrated by DYNAmore using a mix of test data and simulations. So for transparency, we inform the user in this metadata and comments that a portion of these curves until uniform elongation is derived directly from test data and that the subsequent portion is purely an extrapolation. So these curves can now be exported to MAT24 in LS-DYNA. The GISSMO data is all placed under a parent logical attribute, yes or no. So this allows users to directly search on materials that have any GISSMO data. All data for GISSMO are included as metadata, again, as provided by DYNAmore. As part of the metadata, we also include the guidelines for other parameters in LS-DYNA when using this data. And this is as recommended by DYNAmore. So this text is also exported to the material deck. In this case, MAT add damage GISSMO in LS-DYNA. So the numerical data and the metadata pertaining to this GISSMO section is all exported through the LS-DYNA exporter. So the rest of the datasheet is supplemented with data from GRANTA. So we follow our standard data collection procedures and populate the key property data for selection, simulation, and design. This includes composition, equivalent grades, elastic properties, thermal properties, electrical properties, as well as sustainability data for carbon footprint and embodied energy. So in case you noticed, the records currently have been given a very generic name, as is the case with the MI Pro database. But the equivalent grade attribute, it contains the very specific grades this material is available in. And the metadata for GISSMO contains the information on the exact material grade that has been tested, in this case, the voestalpine grade. As such, any such information, we believe, aids in traceability and transparency of the data is captured in the metadata. Excuse me. Yeah. So it does not contain any proprietary information on the actual calibration procedure employed to generate this data. But otherwise, it contains all the data that is necessary to understand and implement this data within a simulation. And that's basically it. So I hope I have given a decent introduction to GRANTA and our new GISSMO data. This data will officially release in a few months' time, but the internal feedback has been very positive, and we believe that through MI Pro, we can introduce GISSMO data to a wider market of smaller OEMs with, say, limited or restricted access to the full crash ecosystem. And additionally, through the MI Pro schema, the users can also store their in-house data, test data, if they have any. So on the whole, the introduction of GISSMO data is a key milestone for GRANTA. So many thanks to DYNAmore MCC team for their partnership. And we're eagerly looking forward to continued collaborations with DYNAmore in other simulation areas as well. So with that, I would like to thank Filipe for giving me this opportunity to speak with you today and present at this event. And yeah, thank you all for your time. So in case of any questions or comments or general feedback, please do reach out to me via email. I hope you have a good rest of the day, and thank you.
Okay, thanks, Harika. I think she's trying to so she will hear the thank you, and I think she also heard the applause. Okay, so we have another break. This was a short session, just 1 hour, and we have like now a break till 15:15, so 3:15, which is actually 45 minutes from now. And then we have our last session, and Filipe will talk about the FAQs regarding GISSMOs. Yeah. Okay, so have a break, 45 minutes, and then we see you in 45 minutes again. Okay, thanks. Okay, so welcome back. This is the last session today, or basically last talk. I think it's half an hour, or how many questions did you answer?
I don't know.
Okay, so this is the last session again from Filipe, and he's trying to summarize the most frequently asked questions concerning GISSMO. And I'm not sure if we should do a question and answers afterwards again for the session as usual. Hopefully you answer all the questions before. Okay, so please, Filipe.
Thank you very much. Just one moment. Okay. So thank you very much, Mike, for the introduction. And in this last presentation, I have some hints around GISSMO, coming from experience around over the years, and also some frequently asked questions that we get very frequently. So let's start first with the hints. First hint that I have for general use of GISSMO is try to understand typical strain measures and its values, or their values. I have here the example of the uniaxial bar, just in one dimension. You have the engineering strain given by this formula, and you also have the true strain given by that formula. So we can see that's just a very simple and basic definition. But I've seen over the years quite a few times where this definition was important in order to interpret your results and understand what's going on. So let's just see what values you can have here. For instance, if you have one-dimensional bar under tension, if the bar length, or the length of this bar increases by 10%, the engineering strain is 0.1, so 10%. And the true strain is about 9.5%, so quite similar actually. But if you keep increasing the deformation, for instance, the bar length doubles, so you have for the engineering strain 1, which would mean 100%, but the true strain is 69%. So now the values start really to deviate from each other. And if you triple the length of the bar, well, the engineering strain will be 200%, but the true will be around 100%. So, and why I'm telling this, because when you are working with LS-DYNA, for instance, you have like a side rail like this one, and you're looking at the plastic strain, which is happening there. This is the true strain. And we tend to think as engineers too much like engineering strains. For instance, one example that I can mention is that one user wanted to have a later failure, so he changed the failure strain from 100% to 200% true strain. But what happens is that if you have 200% true strain, it means the engineering strain, it's 640%, so it's quite a lot. So it's a lot of deformation. And trust me, I've seen this more than once, that people are confusing those two concepts. So this is my first hint here. Try to understand this, because it's not difficult and it can help you. For instance, if you get a material card from a supplier, you look at it under tension, you have a failure strain of 300%, that's way too high. 300% true strain, it's a lot. And as I mentioned in my first talk, failure is dependent, strongly dependent on the plastic strain. So it pays off to pay attention to this. And just to make it a little bit more complete, what happens if you have compression? So if this bar is being compressed, if the bar length decreases by 10%, the engineering strain is minus 10%. The true is also around minus 10%. If you have half of the length of that bar, the engineering strain will be minus 50%, the true minus 69%. But if you really compress this bar until it really collapses, then you have the engineering strain minus 100%, but the true will be minus infinity, okay? So depending if you have tension or compression, this idea changes a bit. The second hint that I have is, I saw this quite a few times, that people look at the deformation simulation and they say, oh, that's shear, that's compression, that's tension, just by purely visualizing what's happening there. So my hint is check the triaxiality, because the triaxiality is something, a value that you can measure, that you can see. And sometimes, actually many times, it can be misleading what you see. It looks like shear, it looks like compression, but it's not what's happening in your material. So my hint is check the triaxiality. I have here one example, just looking at LS pre-post, what the triaxiality can be in such cases, yeah. And this can help you a lot to understand what's happening in your model, in your simulation. If you're not using GISSMO, you can do this even without using GISSMO. You just have, let's say, MET24. If you do this, make sure that you set the sig flag to 1 in database extent binary, and then you will be able to visualize the triaxiality in the LS pre-post as well, okay? So this can help you a lot in understanding what's happening in your component. And remember that failure is strongly dependent on the triaxiality. Yeah. So I've seen also a few cases where people were misinterpreting what they had because they didn't look at the triaxiality. Looking at the triaxiality made things a bit more clear. My third hint is to use D3part when working with large models if you want to understand what's happening in a particular component. Just this week, I had one meeting with one customer who was trying to understand why his material is not failing under certain condition. It was a very large model, and that was exactly my suggestion. Break it down in a smaller one, and you can use the D3part function for this. And if you use the D3part through database binary D3part, you can make the output interval a little bit or much more frequent, so to speak. You can even turn off the averaging of the integration points in a shell, because if you look in your D3 plot, you always have the average of the layer, so you can turn this off by doing this. And then you can really debug what's happening in a single component. So you don't have to do this, let's say, for a whole car. You just do this for a single component, and this can help you also to understand what's happening in there. So this helped me also quite a few times trying to understand what's happening in a particular component, if it's failing too much or it's not failing enough, so you can really understand what's happening there. Which brings me to my hint number 4. Use control debug is an option that we have implemented many years ago. And basically, you don't need any options for this. You just put control debug, and then you have it. And in the message files, you will get, as soon as one integration point has failed with GISSMO, you will get the GISSMO failure report like this. So you have information about the PID, where it failed, the shell element or the element ID, the integration point which failed, at which time you have the triaxiality at the moment of failure, you have the triaxiality, the average triaxiality up to that point, and you also have the plastic strain exactly at the point of failure. This can also be helpful to understand why one element is failing. Sometimes you have element erosion in your model and you understand where it's coming from. You can take a look at this, because if it's coming from GISSMO, you will have this output if control debug is activated. Another way to work with this is really getting this information and make a plot like this, where I just got all the integration, the failed integration points, and I put in a plot. It's coming from this example here. And in principle, you're not really seeing which elements are getting deleted or not. Many of them are not deleted, but you have a lot of integration points which have failed. So in this case, it can help you also a lot to understand what's happening, what are the stress states which are interesting. In this case, basically, all triaxialities are interesting, so you don't really get too much information about this. But in some cases, you can see it's concentrated in shear or concentrated in the biaxial case. So this can be quite helpful in trying to understand what's happening in your simulations with GISSMO. I can perhaps make a reference to one case where we had a component test and the force was weird, it was awkward, it was not really matching the result. And then we took a look at this and we realized that we had a lot of failure under compression at very high strains. And we didn't know what was happening there, because it was very, very high, the strains. What's happening? Turns out that the contact was not working properly. We had too much penetration and numerical problems because of the contact, and they were not very clear at the point. once when we used that keyword and we asked ourselves what's happening there, then we could find out it was the contact who was creating some problems. So my big recommendation is to use control debug. Actually, you can have this all the time active in your input text. The recommendation that we can give. Hint number 5, alternative damage. If you're working with a non-linear damage accumulation like this, it happens that the damage value that you get here, for instance, let's say that you have here 30% of damage. Actually, you're not that far away from the point where you would get damage 100% because it's non-linear. At the beginning, it's just accumulating a little bit, but at the end, it really goes non-linear. So this sometimes can be a little bit difficult for us to interpret. How far we are from damage? If you had a linear accumulation, at the same point, you would have a much higher value of damage, like 70%. So it really looks like, okay, it's more critical if you look at 70% than at 30%. On the other hand, working with a non-linear damage accumulation is a good thing for metals. We know they should behave like this. So this is really just a post-processing thing. So that's why many years ago we implemented the alternative damage, which is located in this history variable here. And what it does is it really makes a linearization of your non-linear damage, but just for post-processing purposes, okay? So I have here one example where we had a maximum value of damage of 17%. And if you go to the alternative damage, actually the results are exactly the same. It's just an interpretation thing. We can see that the value now here, the critical one, is 41%. So it gives a better feeling of how much damage you really have in your part. It also makes the contour plot a little bit more visual. You have, let's say, a little bit more of colors. It's a better description. And some customers, they actually even use this as a default. When they are really outputting or visualizing their results, they don't look at the normal damage, they look at the alternative damage just for the purpose of interpreting their results. So it is a hint that I can give you. And of course, this only makes sense if your damage exponent is bigger than 1. If it's 1, you will get exactly the same result for damage and alternative damage.
But the alternative one is always with 1.
Yes, it's actually a linearization. You see here, the alternative damage is d to the power of 1 over n. So it's a linearization of the damage based on the exponent that you have. So it's exponent independent. Yeah. Okay. Another hint that I can give you is using LS prepost to create strain triaxiality paths. It's a feature that I use quite often. It only works for shells, but basically, if you have in your extent binary, you have sig flag set to 1 and EPS flag set to 1. You just can go here to post and to FLD, so it's not very intuitive. But here, if you go to that point and you select triaxiality and strain path, and you click in an element, you will generate this kind of plots with the strain over triaxiality very easily and automatically. You can even select more than one element. So I use this feature quite a lot, actually. It's very practical. Not everyone knows about it. That's why I'm putting here as a hint. Just one further hint, which is not here in this slide, is that normally we animate until we can find what is the critical element, and then we select that element. And if you just click on plot here somewhere, it will make you the strain triaxiality path from that point from the animation up to the end. So after you selected the element, you have to rewind your animation so that you have the full plot for the full path if you want to see that for the whole way. Yeah. So again, as I said, it's a feature that I use quite a lot. Another hint that I can give you, if there's something that I learned over the years, is that hardening curves are important. The quality of hardening curves are important. So I have here some best practices that come from my personal experience with this for metals. And sometimes in our support, we see some of these things which are not being respected. So I wanted to give you some insight on this. For instance, make sure that your hardening curves always start at plastic strain 0, because otherwise you might have some extrapolation in a different direction. You might get to bad results if you don't do that. And this is a mistake that we see actually quite often, that the hardening curves are not starting at 0. Ideally, it should be smooth and monotonic. It doesn't have to be monotonic, but ideally, yes. There are some cases where this monotonic behavior is not necessary, or we cannot work with them. And one good way to check the smoothness is just doing the derivative. So here I have one ideal example where you can see that the derivative is very smooth. Normally, if you look at the hardening curve, you don't see that if it's really smooth or not. When you do the derivative, sometimes you see it's really oscillating. And sometimes it's crossing, the derivative is crossing the hardening curve more than once, which means that, well, when the derivative curves crosses the hardening curve, that's your necking point. And if you have multiple crosses, basically the necking point is not well defined. So try to make sure that the derivative is as smooth as possible. We recommend using at least 100 points, but this can vary. I know customers are working sometimes with much more points, sometimes with less points, but that's just a best practice if you don't know where to start. If you're working only with one curve, try to make the density of the points larger at the beginning than at the end, so you really get some more accuracy. And try to set up your curve at up to a plastic strain of at least 100%. As you saw today, 100% plastic strain, it's actually already a lot, but then you're making sure that your extrapolation, or up to that point, you have a good curve. I've seen on support some curves which stop at, I don't know, 5% or 7%. Actually, you can make more than this. And all these measures will not guarantee, but they will help you in achieving a robust model in terms of if you make small differences in your model, it will not start to oscillate a lot. It does not guarantee that, but it helps definitely to get that. All right, so those were the hints, and now we have some FAQ, some frequently asked questions. One is about solids and shells. We're coming to that in a minute. So, question that we get a lot, which experiments do I need to calibrate GISSMO? It's difficult to say exactly because it actually depends on the application, okay? But if you're working in automotive crash with shell elements, we've been working with those experiments. So if you want to some guidance, you can start here. But this is more like for automotive crash and shells. If you look at the presentation that David gave us before, for the solids, he's using a few more tests. So it really depends on the situation. But at least those specimens here, they have proved to be a reasonable compromise between accuracy and cost when generating a GISSMO card. But again, this is really problem and application dependent. How do I calibrate a GISSMO card? A question that we get a lot. And of course, it's not easy actually to calibrate a good card. And also, but that's the method that we propose. That's the method that we also use. Actually, we do basically 3 sequential steps. First, we calibrate our plasticity model, which means it's, for instance, if it's MET24, it's just a hardening curve. When that's done, we go to the next step where we calibrate our GISSMO parameters for a fixed element size, like 0.5 millimeters, for instance. And when that's done, then we go to the third step where we do the GISSMO regularization. So it's the element size dependence. You can work in a different way. I know that some users are using different methods, but this is a method that we use and it's actually quite good. Just bear in mind that you are making assumptions. For instance, if you're using MET24, you are assuming that your material is isotropic. If you're working with shells, you are assuming that you have a plane stress state and so on. So not always it's possible to really get a good agreement with experiments. but mostly because of the assumptions that we have there. And one of the questions that we also get sometimes is, can we fully automate everything? At least in my personal experience and opinion, we are still not there that we can fully automate calibration in order to have good accuracy, to really get a good calibration. Perhaps one day we'll be there, but right now, fully automated, we still don't get it done. This is also a question that I got quite a few times. Do I need an instability curve, ICRIT? How do I calibrate it? You don't need it, and especially if you're a beginner in GISSMO, I typically recommend do not work with instability because it makes things more nonlinear, more difficult to calibrate. Yeah. So if you don't want to work with that, then just set decrete to 1 or to a value like 0.95 or so. But if you want to work with this, there are different methods. I'm showing here 2 methods that we've been using now over the years. Basically, if you make the derivative of the hardening curve, where you have here the crossing of the curves, that's your necking point. And this can be exactly the point where you start your instability curve. So one typical method that we use is that we make a parabolic approach, coming from that point on to the left and to the right. You can also use a criterion like Swift, for instance, okay? But there's no clear method how to do this. Depending on the material, depending on the situation, we use a different approach. If you use ICRIT, you also need to calibrate the fading exponent. In my experience, values between 1 and 5, they are typical. Above 5, you start really to have almost no influence in your simulation. Question number 4, now we get it. Can I use the same material card for shells and solids? Well, just speaking from a point of view of the software, you can. There's nothing preventing you. LS-DYNA doesn't know if the material card was calibrated for shells or for solids. But in a general sense, you shouldn't. Yeah, but it depends on the case. So one good approach is, for instance, simulating a tensile test with shells and then solids using the same material card. And then you can get a feeling how much this effect will be. I've chosen here one example where the difference is rather small, but if this is small or not, it's also a question of, I know customers who would say, this is quite acceptable. Other would say, that's not acceptable. I want to have much closer. So we cannot decide this for you. So yeah, actually, you shouldn't, but you can. In some cases, the differences will be small. In some cases, the differences will be very large. You really have to just try this in a simulation. And some customers, they even have this like automated. For each material card, they have already in their database a simulation with shells, simulation with solids, and then you can compare in the database what the answer is or what the difference are. We also get this question then, okay, I have a material card for solids, but I made it for TETs. Can I use this for hexes? Same thing. Generally, you shouldn't, but again, it depends on the case. So here I really choose 2 cases. One is a brittle material, very brittle, actually, and you see no difference at all. So basically, in that case, you can use TETs or hex. You have exactly the same result. And then I have here a ductile material where you can see here, this is the answer with hexahedra, and this is the answer with tetrahedra, and they are different, quite different. Actually, with the tetrahedra, with that card, you can see it fails way too late. So if you use that material card, which was intended for hexas, with tetrahedra, then you get just completely different results. So you cannot just say beforehand, use this, it will work. Each case is one case. That's how it is. Yeah, and just one thing that we noticed over the years, if you do regularization for TETs or for hex, for the same material, typically the regularization factors are different. Yeah, they can be quite different actually. So another argument against using exactly the same material card. I get this question quite a few times. What is a good value of damage to indicate the probability of failure? People ask me, okay, damage equals to 1, that's when you have failure. But should I go up to 0.7 and then I have some risk, 0.8, 0.9? What is the value that I should use there? And actually, if you think about that's not what GISSMO is intended to do. GISSMO is deterministic, so it really assumes that you have one material, and when you have damage 1, you will have failure. If you have something else or below 1, there's no failure. That's what it is. But physically, probability of failure, you can have different sources, and I understand that people are aware of that, or they want to consider this. But one of the sources is definitely material scattering. You have different, or you have variations of the material. So I believe that actually considering this material scattering in your simulations will actually be a better way to really talk about the probability of failure. A typical approach in the industry is using a so-called min, mid, max approach, where you have one card, which for instance like is min, in the tensile strength and in the failure strain, but also max in the strength and on failure strain. And with that generation, that variation, you can really see what is the variation because of material scattering. Question number 7, this I think we get a lot when we make some material cards from at the MCC. Customers, they look at our results, our experiments, they look at the engineering stress strain curve, and they see, okay, I see here 31% failure strain. They look at our calibrated failure curve. They see here for 1/3 is 100%. Why these values are so different? Well, actually, first, this is the engineering strain. That's the true strain, so they are different values. But not only that, when we calculate this engineering strain, normally we have a certain strain, a gauge length, which can be different depending on the specimen. It could be 10 millimeters, 30, 80 millimeters, and so on. So the reference length where it's really determined is different. And when we're looking at the true strain at the element level, we typically have a different value, for instance, element size 0.5. Okay, so that's where it's coming from. Question number 8, if I have regularization, will I have the correct results for any mesh size? I get this question also quite a lot. And the answer is no, because the regularization is intended really to deal with the spurious mesh dependence. And here I have one example where the spurious mesh dependence was really active, and without regularization, I didn't get a crack like in the experiment. But with regularization, I did have the crack. So in that case, regularization was important. But sometimes, if you use 2 or 5 or 10 millimeters, you will not describe the geometry properly or not its deformation. In that case, regularization cannot do anything for you because it's a geometrical thing. So here I have an example of a wheel, which is subjected here to some compressive loading. And you can see here, this V shape you can only get with the fine mesh, 2.5 millimeters. The same thing for this force peak. So there is a case where regularization cannot do anything for you in that case. And finally, last question today. I get this also sometimes. I see damage equals to 1 in my simulation, but no element erosion. Why? Typically, this happens when you're working with shells, and the NUMFIP is not 1. So what it means is that the NUMFIP criterion was still not reached, still not achieved. That's why you see damage equals to 1, but it's still not eroded, because typically people look at the maximum value in the shell element through the thickness. So that's why they see the 1, they say, why it's not really failing? That's the explanation. From a generic point of view, this means that what can be interpreted as the prediction of a surface crack, so it is starting to fail, but not really failing. And some people also ask me, okay, but it should fail. I have experiments. It's really almost there, but it's not failing. What can I do? One hint is if you want to provoke element erosion in such a case, just reduce NUMFIP, and then you will have your crack for that case. Yeah, you can do this to make some studies, for instance. Yeah. All right, I think I'm quite on time. That was my presentation. If you have questions, you can ask them.
Yeah, there have been some questions actually online. So the first question was, can you please discuss the average triaxiality? What is it used for?
Yeah, let me see how can I explain this the best way. Yeah, the average triaxiality, unfortunately, I don't have a formula here, but it's more like sometimes, let's take this example here. Sometimes some integration points, they really are mostly under tension in your simulation, and they have a very high value of damage. Then suddenly, just before they fail, they change the stress state, I don't know, to compression. So just the last step to generate that last piece of damage is in a completely different stress state. So if you just look at the final triaxiality, this will be misleading because you think that the element is failing under compression. But it was most of the time under tension. That's why we use the average triaxiality in order to see what was typically happening in that element. That's the idea of it.
So it's like a time average thing, or
it's
like
not over time. It's
incremental.
It's incremental over damage accumulation.
Okay.
Because if it's elastic, it doesn't make any sense to make an accumulation.
Okay. Okay. Cool. Okay. One more. Wait, I have to unlock that door. Okay. You showed some tests for calibrating GISSMO model. Is it also for plastic, the procedure?
No, it's not. I just had a discussion about this in the coffee break. Let me go to this. That's much further away here. For instance, if you do a notch tensile test for an unreinforced plastic with this, the material starts to deform so much that you get tension. If you do the shear test like this for an unreinforced plastic, it starts to deform so much that you have tension. So it doesn't make sense to use those. That was the purpose of the presentation that Sergio gave today, that we use only the tensile tests and the bending tests in order to get a triaxiality dependent curve.
Okay, good. Okay, are there any questions from the audience here? I kind of online hijacked a little bit, but something here? No? Okay, I think on slide 10, you said something about the hardening curves. It's that you should have a higher density for smaller plastic strains. I didn't get this point.
At the beginning here, if you're only using one curve in NMAT24, it really takes the curve that you have there. And in my experience, you can get better accuracy if you really define this part here very accurately. And typically it's very non-linear, so that's why we suggest or recommend use a higher density of points in that part.
Density of points, okay. I was thinking about material density, was like, what?
No, density of points.
Okay, that makes sense then.
The density of the curve, okay, I would change that sentence.
Okay. Okay. And just a general question, the frequently asked questions are like actually support tickets you got?
It depends on conferences, support tickets, phone calls.
And which was the number one question you get most often? What would you say?
Tobias, help me. I think that right now is this one. Can we use the same material card for shells and solids?
Okay.
We got requests to make DYNA to work with the same material card, independent of the element type. This is a very popular one.
Yeah. And I was expecting also the true strain, engineering strain thing.
No, we don't get that as a question too much. We get this more like people are wondering why the results are the way they are, because they are confusing those two. As I said, like the guy who changed from 100% strain failure strain to 200% and was not failing, and he said there's a bug in LS-DYNA, and said no, it's it's just misleading how you're thinking.
Okay, no questions here. Okay, so I think then we're already at the end of the day. I think I have just not much to say here, except for this one here. So as a reminder, So, I mean, first of all, thank you everyone for attending. Also for the people online for attending, also for engaging actually online, posting questions in the chat. I also remind you for our conferences, the German conference in 16th of October here in Stuttgart. And then we have the international one in October 22 and 23rd in Detroit. So if you want to go to America, I think this is a good choice. And still, you can contribute. And with that being said, I think, thank you everyone. Thanks for listening. Thanks for sharing. Thanks for engaging, and see you soon next time. Okay. Thank you everyone. Thanks.